Let us spend a little time today digressing to a topic in dynamical systems more properly taught in courses on physics, namely Hamiltonian systems, and I would like to bring out to you how special Hamiltonian systems are, and we studied Hamiltonian systems from the point of view not so much of mechanics as of our general study of dynamical systems and nonlinear dynamics. Before we talk about Hamiltonian systems, there is another class of dynamical systems which I would like to dispose of, or at least mention very briefly in passing, and perhaps we might come back to such a system a little later in the course, and this is a class of dynamical systems called gradient systems. Recall our particular kind of dynamical system that we have focused on, namely those which satisfy autonomous coupled differential equations of the form f of x, where f is a prescribed vector field. It is a function which has really got n components in n dimensional phase space, f1, f2, f3 up to f sub n, and these are functions of the coordinates or the variables x1, x2 up to x sub n. Therefore, to specify the dynamical system you have to specify a vector field at every point in some region of phase space. A gradient system is one where this vector field has a very special form. If this vector field is of the form the gradient of some scalar function of the variables x, I call this a gradient system. What is special about it, of course, is the fact that instead of specifying a vector field which means all its components, n functions f1 through to xn, f sub n, we need to specify just a single scalar function phi, and everything else, all the components of f are determined in terms of this single scalar function phi. So clearly it is a very special kind of dynamical system. Not all dynamical systems can be written in this form, but those that can clearly enjoy a little superior status among dynamical systems, because a single scalar function suffices to tell you the flow at all points. Now of course the component of this, if I take the ith component, this implies that xi dot is delta phi over delta xi, and phi is a function of the variables x. Okay. That is what is meant by a gradient system. If you give me the function phi and I set phi of x equal to a constant, it would in general be a surface in this n dimensional phase space. So if schematically this is what the surface looks like at a particular point x, and this corresponds to the surface phi equal to a constant c, say, then what is the direction of the gradient of phi at this point? The gradient is defined as the normal derivative. The gradient of any scalar field is the normal derivative. It is the direction in which this function phi has the maximum rate of change, that direction along which it changes most rapidly. Therefore it is normal to the direction of the level surfaces of phi. So if phi equal to constant is a surface, the level surface phi equal to constant, then this is the direction of the gradient of phi at that point, which means the flow lines or the phase trajectories of a gradient system are always normal to the level surfaces phi equal to constant at each point. Now that is a useful fact to know. We do not come across too many gradient systems, they are somewhat rare in a certain sense, but when they do occur, then it is very useful to give a geometrical interpretation for the flow lines in this sense, namely the lines phi equal to, the flow lines are normal to the level surfaces of the scalar function phi, single scalar function phi. There is another very important class of dynamical systems called Hamiltonian systems, for which once again a single scalar function determines the vector field f on the right hand side. And now let me define a Hamiltonian system. These are systems which are always even dimensional in a very specific manner. They are described by a set of dynamical variables which occur in pairs, and therefore the total number of variables is always an even number. The first n variables are generally denoted by the q's, q1, q2 up to qn, and these are generally usually called generalized coordinates. And along with them go a set of variables p1, p2 up to pn, which are called generalized momenta. Therefore, the full set of dynamical variables x is a set of 2n variables q1 to qn, p1 to pn, 2n dynamical variables. The phase space of a Hamiltonian system is always even dimensional. It is conventional to call q's, the generalized coordinates, degrees of freedom. So this system has n degrees of freedom and it has 2n dynamical variables. Something very special connects each q to its corresponding p, called its conjugate momentum p, and that is a structure called the Poisson bracket, and I will define this as we go along very shortly. For the moment we will use this terminology which says that the q's and p's are conjugate to each other. q3 is conjugate to p3, q4 is conjugate to p4, and so on. The more strict term is canonically conjugate in a standard manner, and we will explain as we go along what we mean by this. The equations of motion are of particular interest. They are called Hamilton's equations of motion, and the most common occurrence of Hamiltonian systems is a set of particles moving, for example, under the influence of forces which they exert on each other, conservative forces which they exert on each other, or a set of particles moving under the influence of some conservative external force, or both. Mechanical systems very often turn out to be Hamiltonian systems in the absence of friction, in the absence of dissipation. So Hamiltonian systems will, in the sense we understand it, will be conservative dynamical systems. There will be special cases of conservative dynamical systems, and the equations of motion which correspond to our dynamical equations go by the name of Hamilton's equations, and they read as follows: qi dot is delta over delta pi of a certain scalar function h of all the q's and p's in general, and let me abbreviate that by just writing it as q comma p. That stands for all 2n variables in general, and this is true for each I from 1 to n. qi dot, and the rate of change of pi is again given by the partial derivative of the Hamiltonian, but with respect to the conjugate generalized coordinate qi with a minus sign, and this set of equations is valid for each I. It is not a gradient system, because the gradient system would imply, a gradient system would imply that each time derivative of each dynamical variable is the partial derivative of some scalar function with respect to the same variable, but that is not happening here. The time derivatives of the q's are partial derivatives with respect to the conjugate p's and vice versa, but with a minus sign, and this minus sign is crucial, it is very, very important. This is the general structure of equations when you look at particles moving in a potential, for instance. Yeah, there is a question.
Hello. What exactly is are these properties, or what exactly is defined?
The question is, where do these things come from? This is the definition of a Hamiltonian system, but as soon as I finish defining this, I will go back to ordinary mechanics and show you that ordinary mechanical problems in the absence of frictional forces, these are the defining equations, these are Hamilton's equations, they define a Hamiltonian system. The original motivation was of course the observation that Newton's equations of motion in the case of conservative forces are essentially Hamiltonian equations, and this is a generalization of the idea which one already has from Newton's equations of motion. So let me do this in a formal way, and then we go back in a minute and see that ordinary mechanics is indeed a special case of Hamilton's equations of motion with a specific prescription for the Hamiltonian function. But right now I am doing this in a very abstract way, I am simply saying that if a dynamical system is even dimensional and has this kind of structure with certain additional properties which I am going to write down regarding the way the q's and p's are related to each other, then it is called a Hamiltonian system. Okay. So let us step back and ask, is this a gradient system? No, not as it stands, but you still have this wonderful property that the entire vector field on the right hand side is actually defined in terms of determined by a single scalar function, the Hamiltonian function. Okay. That is going to cause a great deal of create a lot of simplification, it is going to lead to a lot of simplification and very interesting properties. Now let us go back and ask, what happens if I take a single particle which is non-relativistic, ordinary Newtonian mechanics, moving in some conservative potential or field of force? What would you say are the equations of motion? A single particle moving in some potential. I could write down Newton's equations of motion, and the way to write it down in our language is to say that the mass times the velocity, which is dr over dt, is the momentum p, and the rate of change of momentum dp over dt is equal to the force on the particle. If this force is time independent, no explicit time dependence, and depends only on the instantaneous coordinate of the particle, then it is some f of r. And if this force is conservative, which means it is the gradient of some scalar potential which has the connotation of a potential energy of the particle, then this is equal to minus the gradient of a potential v, which is a function of the coordinates of the particle. This is what you would write down as the normal equations of motion. I have just written Newton's equations down, but as a set of coupled equations. Dr over dt is p over m, I could bring this to the other side, and dp over dt is some function of r. It certainly is a dynamical system in the sense we understand dynamical systems. What is the dimensionality of the phase space here? It is 6 dimensional because 3 coordinates and 3 momentum variables, so 6 coordinates, and it is exactly the structure that we had. X dot is some f of x, some vector field on the right hand side. So we have written it as 2 coupled vector equations, 3 dimensional vector equations in this fashion. The question is it of that form? Is it of this form at all? Can we write it in the form of Hamilton's equations. By hindsight we know we can, because we know that in ordinary mechanics with conservative forces the Hamiltonian of the particle has the connotation of the total energy of the particle, which is the sum of its kinetic energy and its potential energy. So we write H as a function of R and P, and these would be Q1, Q2 and Q3 in this case, and this the components of P would be P1, P2 and P3. If these are Cartesian components, then this is equal to P squared over twice the mass of the particle plus the potential V of R. And if I call these components Q1, Q2 and Q3, and similarly this has components P1, P2 and P3, it is immediately clear that these equations here really imply that Qi dot is indeed equal to delta H over delta Pi, because if I want to find out what dQ2 over dt is, we know from this set of equations here that dQ2 over dt is P2 over m, and that is precisely delta H over delta P2, and it also tells us that Pi dot is minus delta H over delta Qi. Since the potential energy depends only on the coordinates, when you differentiate with respect to the coordinates in Hamilton's equations, you end up with the corresponding component of the force. So this is an example of a Hamiltonian system, and the way I have defined it there, in general it generalizes the same idea to n degrees of freedom. And the simplest way of thinking of a Hamiltonian system is to look at the special case of a set of particles moving in a conservative field of force. And that is an example, the standard example of a Hamiltonian system. There are many other Hamiltonian systems as well, but that is the simplest example. So Newton's laws of motion for conservative systems are definitely Hamiltonian. The prescription for writing the Hamiltonian down in conventional mechanics is fairly straightforward. You start with the Lagrangian of the particle and then you make a certain transformation and go over to the Hamiltonian, and generally in elementary problems it turns out to be the sum of T plus V. It is the sum of T and V, but T is the kinetic energy and V is the potential energy. That is the way we have written it down here, but it is much more general than that. This scaffolding is not necessary. A Hamiltonian system is defined by the set of equations, Hamilton's equations that I wrote down, the general equations, together with a certain connection, a certain structure called the Poisson bracket relationship between the Q's and P's, and let me define the Poisson bracket. Given the dynamical variables Q1 through Qn and P1 through Pn, if I look at any function of these dynamical variables, and let us call them A of Q and P, and any other function of all the dynamical variables B of Q and P, then the Poisson bracket of A with B is denoted by curly brackets A comma B, and by definition it is equal to a summation over all the degrees of freedom 1 to n delta A over delta Qi delta B over delta Pi minus delta A over delta Pi delta B delta Qi. This is the definition of the Poisson bracket of A with B. we need to understand a little more about the structure involved here, but it is these partial derivatives in this particular combination. If the Q's, by assumption the Q's are independent of each other and the P's are independent of each other, then it follows, if these are independent dynamical variables, it follows that delta Qi over delta Qj is 0 unless I equal to j, in which case it is equal to 1. Therefore, this is equal to the Kronecker delta. Similarly, delta Pi over delta Pj is delta Ij, because the P's are independent of each other unless I equal to j, in which case it is identically equal to 1. And the Q's and P's are independent dynamical variables. So delta Qi over delta Pj is always equal to 0. So you have two sets of dynamical variables, half of them are regarded as generalized coordinates and the other half as generalized momenta. They are independent dynamical variables, you need all of them to describe the dynamical system. So this is not surprising, and the fact that this relationship or that holds good simply says that different Q's are independent variables, you need that many independent variables to describe the system. Once you have that, you could ask what is the Poisson bracket of a particular Q with a particular P, and let us figure that out. So what is the Poisson bracket of Qk with PL, for instance? What is this equal to? All you have to do is to plug it in here and do a summation over I and compute what the answer is using the statements we had earlier about the P's and Q's. So what do you get? Well, this is going to become a delta Ki and this is going to become a delta Li. So it is 0 unless K is equal to I, and this term becomes 0 unless L is equal to I. So the answer is delta KL, because this term would anyway be 0 if you differentiate a Q with respect to a P or a P with respect to a Q, the answer is 0, and therefore it is equal to the Kronecker delta. What is the Poisson bracket of Qk with Ql? Both these quantities are now Q's in the numerator and at least one of these will vanish, and therefore this is 0, and the same is true for Pk with Pl. This set of relationships between the generalized coordinates and the generalized momenta of a dynamical system, of a Hamiltonian system, are called canonical Poisson brackets. So these are the canonical or standard Poisson bracket relations. You might ask, why am I defining a Poisson bracket? Why is this? What is the use of this? And we will see very shortly what the practical use of this is. But meanwhile, this relationship here, this way of defining Poisson brackets, has got mathematical structure to it, very deep mathematical structure. Notice it is a bilinear operation in some sense. You give me two functions A and B of the dynamical variables of a Hamiltonian system, and I do something which involves both of them. It is a bilinear structure. In general, the right hand side is some other function of all the dynamical variables, and it has also got certain interesting properties of the following kind. A with B plus C, if you took two functions, the sum of these two functions as a second member of the Poisson bracket, it is quite clear this is equal to A with B plus A with C. it is immediately obvious that this is so. If I multiply B by some constant which is independent of all the dynamical variables, then of course the constant comes out and A with KB is equal to K times A with B, where K is some constant. And this quantity is also antisymmetric. So you have a natural antisymmetric bilinear structure here. Yes.
This canonical relations, they are coming up just because the coordinates are independent.
Absolutely,
So
absolutely. There is nothing great about it at this stage, but the fact is that these things have enormous implications. Once you identify a Hamiltonian system, then you guaranteed certain relationships automatically. So what we have done is the other way about. I started with mechanical examples and I told you Cartesian coordinates are independent of each other, and I wrote down certain relationships between them, but the fact is that structure generalizes to much more general context than just the usual ones you are used to. Okay. So it is simply that it is a very useful and a very general framework for understanding a huge class of dynamical systems, of conservative dynamical systems. Right now we are talking about some mathematical properties of Poisson brackets, and we are writing down relationships which are fairly trivial. They follow fairly straightforwardly from the independence of the coordinates and the momenta between each other, plus the canonical Poisson bracket relationships, but these have deeper implications, as we will see. What is the Poisson bracket of A with a product of two functions? So if I took A with BC and asked what this is equal to, you would have to use BC here and BC here and use the chain rule of differentiation repeatedly, and then it is a simple exercise to show that it is A with B times C plus B times A with C. This is a chain rule for differentiating functions, that is all that has been used, and then it leads to an identity of this kind. What would this be? What would AB with CD be equal to? What would you get on the right hand side? You would get 4 terms. So first treat AB as a unit and use this formula for decomposing it into Poisson brackets of AB with C and AB with D, and then use the formula again for decomposing this into 2 more terms. So you get a set of 4 relationships. So this is 4 terms on the right hand side. There is one more property of Poisson brackets which is crucial importance, and that is the following. If you took 3 functions A, B, C of the dynamical variables and computed A with the Poisson bracket of B with C, and then took the Poisson bracket of A with this plus the Poisson bracket of B with the Poisson bracket of C with A plus the Poisson bracket of C with the Poisson bracket of A with B, what would you guess is the answer? It is 0. It turns out to be identically 0 on using this property. So there is this antisymmetry when you take 3 of these guys, and the antisymmetry of the Poisson bracket leads to this property. It is easy to establish. Do these properties, you have got a set of objects A, B, C, etc., which are functions of the phase space variables in a Hamiltonian system, and among those functions I have defined a certain bilinear structure called the Poisson bracket. I take two of them at a time and I create something, a new function. That function has this antisymmetry property, and it also has this property which is called the Jacobi identity, and it has the usual properties such as A with the Poisson bracket of A with a scalar times B, constant times B is the constant times that of A with B, the Poisson bracket of A with B, it has the antisymmetry property, and it has the property A with B plus C is A with B plus A with C. Does this remind you of something? Does this structure remind you of something? These 4 properties, do they remind you of anything else, any other example where you have exactly the same sort of properties? Yes? If you took ordinary vectors in 3-dimensional space, in Euclidean space, and you took the cross product of 2 vectors, what happens then? Do they have identical properties? If I took vectors A, B, C, etc., and I computed the cross product of 2 vectors, is this not equal to minus B cross A? And is it not true that A cross some scalar times B is K times A cross B? And certainly this is true this is true too. And is this true? If I replace the Poisson bracket operation by the vector product or the cross product of 2 vectors, is it not true that A cross B cross C plus cyclic permutations turns out to be 0 identically on the right hand side? So exactly the same set of properties mathematically, a bilinear operation which is antisymmetric satisfies these properties and satisfies the Jacobi identity. Anything else? Can you think of any other structure which does exactly the same, any other class of objects which have similar properties? Suppose A, B, C, etc. were square matrices, n by n matrices of some given order, and instead of the Poisson bracket, instead of A comma B as the Poisson bracket, I replaced it by the commutator of the 2 matrices. This stands for AB minus BA. Then the commutator of 2 matrices is antisymmetric. The commutator of A with B is minus the commutator of B with A, and this property is valid for commutators, and so is this. Any set of elements for which such a bilinear product or bilinear operation exists satisfying the antisymmetry property, these properties as well as the Jacobi identity, is called a Lie algebra. So it says functions of the dynamical variables of a dynamic Hamiltonian system form a Lie algebra under the Poisson bracket operation. A very useful concept. We are not going to deal so much with the algebraic properties here in this course, but it is a useful thing to know that there is something deeper, a deeper mathematical structure to Hamiltonian systems under the Poisson bracket operation. So that is responsible. A lot of the properties actually are mathematical properties which have physical implications, which follow from this Lie algebraic structure of functions of the dynamical variables under the Poisson bracket operation. There is one immediate use of the Poisson bracket, and that is the following. In conservative mechanical systems such as those determined as where the Hamiltonian is simply determined as the kinetic energy plus the potential energy, we know that the energy is a constant of the motion. I now show you that the Hamiltonian itself for autonomous systems is a constant of the motion identically, and that is easy to see, because if I start with h as a function of all the q's and p's and I compute d over dt of this quantity, this is equal to, by definition, since it is a function of the q's and p's, this is equal to a summation over the degrees of freedom delta h over delta qi multiplied by qi dot plus delta h over delta pi multiplied by pi dot. Since it is a function of the independent variables q1 to qn and p1 to pn, its time derivative, total derivative, is just this set of partial derivatives multiplied by these total derivatives. But now we use Hamilton's equations of motion, therefore on a solution set, on a solution of the equations of motion, this becomes equal to a summation delta h over delta qi, and what was the equation of motion for qi dot? Delta h over delta pi plus delta h over delta pi, and what was the equation of motion for pi dot? Minus, the all important minus, and of course this is identically equal to 0, which implies that the Hamiltonian of a Hamiltonian system, an autonomous Hamiltonian system, is a constant of the motion. You will appreciate the importance of that relative minus sign in producing this result. What is the equation of motion of any function of the dynamical variables? That too can be written in a very simple way, and that will bring out the use of the Poisson bracket. So let us suppose A is a function of the q's and p's, and I ask what is the rate of change of this function of the q's and p's, and I use exactly the same technique as I used earlier, and what would this become? This would become a summation from I equal to 1 to n delta A over delta qi times qi dot, but qi dot is delta h over delta pi. I put that in, pi plus delta A over delta pi times pi dot, which is minus delta h over delta qi. So they get minus but what is this equal to? The Poisson bracket of A with h. Now that is a remarkable fact. It says the rate of change of any function of the dynamical variables is just the Poisson bracket of that function with the Hamiltonian of the system. That tells you the fundamental role played by the Hamiltonian. Of all the functions of the dynamical variables of such a system, the Hamiltonian is predominant, plays a fundamental role because it controls the rate of change with time of every other function. When is this a constant of the motion? Yes, when A Poisson commutes with h, when the Poisson bracket of a function with the Hamiltonian is 0, if it vanishes identically, then the function is a constant of the motion. and the converse is true as well, as long as we are dealing with autonomous Hamiltonian systems. Of course you could generalize Hamiltonian systems to non-autonomous systems, and then this is no longer true, because if you have a non-autonomous, and let me take a digression for a second and talk about non-autonomous systems, although would imply that there is also explicit time dependence on this side. What would happen then? What would happen then? What would the right hand side be modified to? Plus the partial derivative of h with respect to time. The explicit time dependence gets differentiated, and of course this portion vanishes identically, and you are left therefore with is equal to delta h over delta t, and if h is non-autonomous, that right hand side is not identically 0, and therefore the Hamiltonian is not a constant of the motion. Not surprising, because it is actually explicitly a function of time, and it is not a constant of the motion in this sense. What happens if I consider a function a of the dynamical variables which also has an explicit time dependence, independent of whether the system is autonomous or not? So independent of this, I consider a function which has got explicit time dependence. What should I add on the right hand side? I should add plus delta a over delta t, and therefore it is this plus delta a over delta t. We need to modify this statement then. We already saw that you could have constants of the motion which had explicit time dependence, because the time dependence from the explicit t dependence could be cancelled by that of dynamical variables, the other dynamical variables in this combination. So we now come to the conclusion that a of q p t is a constant of the motion provided a comma h is equal to minus delta a over delta t. So if the right hand side vanishes, then the total derivative of this function with respect to time vanishes, and you have a constant of the motion. So this is the test. This then is the test of when something is a constant of the motion. We are going to look at some other remarkable properties of Hamiltonian flows or Hamiltonian dynamical systems, and the most important one of them for our purposes is the fact that it is a conservative system in the sense of what we meant by a conservative system, namely that volume elements do not change in phase space under the flow, and let us verify that. Recall that when the dynamical system was given by x is f of x, then this was conservative if del dot f vanished identically, or this was identically equal to 0, then we called it a conservative dynamical system. Well, we now have a Hamiltonian system for which our x is really q1 to qn, p1 to pn. It is a 2n dimensional dynamical system. What is the gradient operator in this terminology in terms of the q's and p's? The gradient operator is one which has components which are the partial derivatives with respect to all the dynamical variables. So it simply stands for delta over delta q1, delta over delta q2, delta over delta qn, delta over delta p1, delta pn. And recall our equations of motion. The equations of motion were qi dot was delta h over delta pi but Pi dot was minus delta H over delta Qi minus. Therefore, if I simply compute this divergence here, it gives us a very simple result. Therefore, del dot F in this case was equal to what? It is equal to delta over delta Q1 F1, but F1 is delta H over delta P1 and so on. So this is equal to a summation I equal to 1 to n delta over delta Q1 Qi delta H over delta Pi. That takes care of the first n contributions to del dot F, and the remaining n are delta over delta P1 times minus delta H over delta Q1 and so on. So you also have minus delta over delta Pi delta H over delta Qi. On using Hamilton's equations of motion. But what is this equal to? It is identically 0, since you can take partial derivatives here in either order. If this function is integrable, then you can take partial derivatives in either order. Therefore, this vanishes identically, which says that Hamiltonian systems have flows such that the volume elements in these systems are preserved in time. The flow is like that of an incompressible fluid, or the volume is preserved in Hamiltonian flows in phase space, and this goes by the name of Liouville's theorem. Or preserved is a better word. Again, a fact of great significance. It is not just volume elements that are preserved. Many other things are retained as constants also under Hamiltonian flows. So it is very restrictive. These conditions, the conditions which are imposed by this set of equations plus the Poisson bracket structure between Q's and P's, are actually very restrictive, and they have very deep implications. There is a very rich mathematical structure to Hamiltonian flows, some of which we will uncover subsequently. Okay. I start by saying it's not a result of this structure. No, not at all. No, it's not a result of this structure. It's not. I'm not saying it's an additional constraint. I'm saying that you define a Hamiltonian system as a set of 2n dynamical variables in which the variables are paired off pairwise, each q with its conjugate p, such that the Poisson bracket of each q with the p with its conjugate p is 1, and the Poisson bracket of each q with all the other variables is 0, and similarly for the p's. Together with that, you specify a certain function of all the dynamical variables called the Hamiltonian, and the equations of motion have this structure. That is my definition of a Hamiltonian system, and from that everything else follows, including the fact that the Hamiltonian is a constant of the motion for autonomous systems, the fact that any dynamical variable or function of any dynamical variable, its rate of change with time is given by the Poisson bracket of this variable with the Hamiltonian for explicitly time independent variable functions, and Liouville's theorem which says volume elements are preserved. Various other things are preserved as well, we will not go into that. For instance, if this is a volume element, schematically you have some volume element of this kind in phase space, in 2n dimensional phase space, you could project this volume element onto each QP plane. So I take each Q and its conjugate P, and that forms a 2-dimensional plane, and I project the shadow of this onto this QP plane, and I take the sum of all these shadows of these areas. So I project onto Q1 P1, Q2 P2, Q3 P3 up to Qn Pn, and I take the sum of all the areas, and it turns out as this volume element flows, not only does it maintain its volume, the size, the magnitude of this volume is not changed, it might get distorted but it maintains its volume, but in addition the sum of all those shadows, those areas, is also preserved, it is also constant. That is a very remarkable fact. So it is not very intuitively very clear why this should be so, but it follows, all these properties follow from the structure of these equations. It is not a gradient system, as you can see, but I could write it as something which looks like a gradient system, and there is a mathematical structure here called the symplectic structure, which I am not getting into right now. Perhaps a little later I will mention a few properties of this extra structure as we go along. And as a prelude to that, let me do the following. Let me define a matrix J, a 2n by 2n matrix with the following kinds of elements. So let me define this J as a 2n by 2n matrix with n by n blocks here, and I have the null matrix here. This stands for n by n null matrix. I have the unit matrix here, and this stands for the n by n unit matrix. Minus the unit matrix here, and the null matrix once again here. So it is partitioned into 4 blocks, n by n blocks, and it looks like this, and I call this matrix J. It is a numerical matrix, it has just zeros and ones or minus ones as the elements. This is a diagonal block here with ones here, and this is a diagonal block with minus ones here. These are null matrices. Then it is not hard to see that the equations of motion in this case, in the Hamiltonian case, which are qi dot is delta H over delta Pi, and Pi dot is minus delta H over delta Qi. This set of equations can be written almost in gradient form, in the form x dot is equal to J times the gradient of H, where by the gradient I mean a 2n component differential operator with components delta over delta q1 up to delta over delta qn, and then delta over delta p1 up to pn. And once I put this matrix J here, then it is nothing but the gradient. This twists in such a fashion that the q's, the rate of change of the q's depends on the derivative with respect to the p's, and vice versa, with a minus sign, and that is the reason for this minus sign here. So if I wrote this x as a column vector, 2n dimensional column vector q1 up to pn, and similarly for the gradient of h, and then multiplied it by J, you would end up with just this. So this J does the required trick of converting the part, the rate of change of the q's will depend on derivatives with respect to the p's, and the p's with respect to the q's, but with a minus sign. And this structure has a name, it is called the symplectic. This matrix J has remarkable properties. What is the square of J? Well, it is immediately clear from this that the transpose of J is minus J, because these guys would go there and those fellows would come here. And what do you think is the square of J? I leave you to figure this out. Incidentally, when n is 1, then a large number of the properties become quite transparent, because then you have a 2 by 2 matrix, which is essentially for n equal to 1 implies J equal to 0, 1, minus 1 and 0, and of course you could square this very trivially. I leave you to figure out what J squared is, then we will look at some interesting properties of Hamiltonian systems in this language. The advantage is that it looks very much like a gradient system, so you can write these things down much more compactly in this form. Okay. And one final comment, we started with mechanical systems and said you have the coordinates and you have the momenta, and they are quite physically distinct from each other. But now in an abstract setting, when we talk about Hamiltonian systems as systems defined by just a set of 2n variables of this kind paired off 2 at a time, then the distinction between what you call momenta and what you call coordinates can be actually lost completely. You could make changes of variables of these dynamical variables in such a way that what looks like momenta initially could turn out to be coordinates, belong to the set of coordinates, and vice versa, provided of course you put in factors for the right dimensionalities of these variables. I bring this up because the conventional notion of momentum as a linear momentum is very restrictive, because after all you could also have an angular momentum. You could have generalized coordinates which are angles, and the conjugate momenta would be angular momenta. So the momentum variables could have dimensions of angular momentum, not necessarily linear momentum, and the generalized coordinates could be angles which are dimensionless, they do not have to be lengths. So the advantage of looking at it this way is that you can go beyond the normal mechanical examples and look at the actual structure of the dynamical system per se, which is very intricate, very interesting, and has very, very crucial properties. So we have seen today, to summarize, that Hamiltonian systems form a special class of conservative dynamical systems, autonomous Hamiltonian systems. Liouville's theorem asserts that the volume elements are preserved in phase space, which conforms to our definition of what we said was a conservative system. The rate of change of any dynamical function of the dynamical variables is given by the Poisson bracket of these variables with the Hamiltonian, and the Hamiltonian itself is a constant of the motion. And the Poisson bracket idea enables us to identify other constants of the motion. So we will take it from this point tomorrow. We had started our discussion on Hamilton's equations of motion and Hamiltonian systems. Let me briefly recapitulate the place where we had got to and then go on from there. A Hamiltonian system, if you recall, had a set of dynamical variables called generalized coordinates q1 through qn, and a set of generalized momenta p1 to pn, 2n of them in all, which we have combined together into this vector x, which satisfy the equations of motion. Qi dot is delta h over delta pi, and pi dot is minus delta h over delta qi, for I running over the integers from 1 to n. For n degrees of freedom, you have 2n dynamical variables, they are paired together, the q's and p's, these are called generalized coordinates and these are called generalized momenta, and the equations of motion are these 2n coupled first order in general nonlinear partial differential equations to be solved uniquely provided you specify the initial positions, the initial coordinates and the initial momenta, all 2n of them. We also wrote this by pointing out that the entire vector field on the right hand side governing the time evolution of the vector x, the phase space point x, is given by the gradient of the Hamiltonian, which is a function of all the q's and p's, multiplied by a certain matrix J, which we had written down, and J was a 2n by 2n matrix with zeros in the first block of n by n block, the unit matrix here minus the unit matrix here and 0 here once again. This is the n by n null matrix, the n by n unit matrix minus that matrix and again the null matrix. The introduction of this J ensures that these derivatives get twisted in the sense that the rate of change of the first n components of this vector depend on partial derivatives with respect to the remaining n, and vice versa with the appropriate minus sign. This minus sign is taken care of by putting a minus here. So a remarkable fact has been achieved for Hamiltonian systems, namely that the entire vector field, which normally would have been some vector field f of x, is now specified by a single scalar function. But this matrix J has remarkable properties, and these are responsible to some extent for the wonderful properties that Hamiltonian systems display. The first of these is the following: we see immediately that the quantity h itself, if I compute its time derivative, this is equal to a summation from I equal to 1 to n delta h over delta qi dot plus delta h over delta pi dot. But then if I substitute for qi dot and pi dot from the equations of motion, it implies that dh over dt vanishes identically on the solution set, on solution sets. In other words, whenever the equations of motion are obeyed, on those curves dh over dt is identically 0, which implies that the Hamiltonian h of q comma p is a constant of the motion and remains unchanged as time evolution occurs. We have assumed that the system is autonomous, so h itself has a dependence on the q's and p's but not explicitly on time. What happens when h has got explicit time dependence we will come back to a little while later, but we are right now looking at autonomous Hamiltonians. In other words, h is a function of all the generalized coordinates and the generalized momenta. Mechanical systems, which are conservative systems in the absence of dissipation, particles moving under the action of forces which they exert on each other and so on, these would be examples of such Hamiltonian systems. There are many other examples of Hamiltonian systems, but right now we would like to develop the theory a little bit more before we look at special cases of Hamiltonian systems. This implies also that the trajectories lie on the surfaces on which h is a constant. So you recall we are now working in a 2n dimensional phase space, and any statement of the form h of q comma p is equal to a constant defines a 2n minus 1 dimensional hypersurface in this 2n dimensional phase space, and you are guaranteed that for any set of initial conditions the motion or the phase trajectory lies on this hypersurface. So this implies the motion lies on the 2n minus 1 dimensional energy surface or hypersurface. I call it energy surface because, as I mentioned, the Hamiltonian generally its numerical values have the connotation of being the total energy of a conservative system. This is not always true, but we will use this terminology because that is the most commonly occurring case, that the Hamiltonian essentially is the total energy of the system expressed in terms of the coordinates and the momenta of the system. Normally one would say that the gradient vector of a scalar is directed normal to the level surfaces of this scalar function, because that is the rate of maximum rate of change of this quantity of the scalar quantity occurs in a direction normal to the level surface on which this scalar function is a constant. But the moment you put a j here, this immediately implies that this velocity vector in phase space is actually directed on the level surface itself rather than normal to it, and that is a major difference between ordinary gradient systems where you do not have this j here and x dot is given by this gradient of some scalar field, and Hamiltonian systems for which the motion actually occurs on a surface on which h is constant for each set of initial conditions. My statement was, yes, I would like to explain this a little more. The statement is, if we had for instance x dot equal to the gradient of some phi of x, then this tells you the velocity in phase space, namely the direction of x dot tells you in which direction x is going to change as a function of time at each instant of time. If phi of x equal to constant on this surface, phi of x equal to some constant, and we are at this point in phase space, then this velocity vector is directed normal to this surface in this fashion. So in the next instant the system moves to some other surface, phi of x equal to a different constant for instance, and the motion is normal to the level surfaces phi equal to constant at each point. On the other hand, for a Hamiltonian system, x dot is j times the gradient of h of x, and h of x is constant on the solution set, which implies that if this is locally the surface h of x equal to c at any point, then this velocity vector is guaranteed to lie on the surface rather than normal to the surface itself. So it continues as time goes on for any given initial set of initial conditions. This motion is restricted to the 2n minus 1 dimensional hypersurface specified by h of x equal to that value of the constant which it has owing to the initial conditions.
The question is, how does that become mathematically obvious by the introduction of g?
This j ensures that the derivative of the first component of x is the partial derivative not with of h, not with respect to the first component itself, but the n plus first component, and the second with respect to the n plus 2th component, and so on. It also ensures that the derivative of the nth component of x, which is p1, is minus the derivative of h with respect to the first component. So this minus sign that this j introduces pairwise ensures that h itself is a constant of the motion identically, because if I substitute delta h over delta pi here and minus delta h over delta qi here, this bracket vanishes identically. Now that is formalized by saying that the introduction of this gradient here, this j here, which makes this not the gradient of h but the symplectic gradient of h, ensures that h itself is a constant of the motion. And this quantity here is called the symplectic. We also saw that Hamiltonian flows have another very special property, and that is any volume element remains unchanged in time. In other words, the system corresponds to a conservative dynamical system. So we also saw that del dot f is identically 0 for a Hamiltonian flow. This implies too that volume elements are preserved as time goes along. They may get distorted, they may get substantially distorted, but the magnitude of the volume of any set of initial conditions in any volume element remains unchanged as time goes on, and therefore Hamiltonian flow is like that of an incompressible fluid in phase space, a fact which will have further implications. What else can we say about Hamiltonian flows? Well, here is where a very important structure called the Poisson bracket gets introduced, and let me define this quantity. If I took any function A of all the q's, the p's, and perhaps of time itself, this is just a function of all the dynamical variables as well as maybe it has explicit time dependence, and asked what is the rate of change of this quantity as a function of time, this becomes equal to, we have done this becomes equal to the Poisson bracket on the right hand side, and therefore the importance of the Poisson bracket becomes very clear now. This is equal to A with the Hamiltonian plus delta A over delta T recall this, and this quantity A is a constant of the motion if this right hand side vanishes, and if A does not have explicit time dependence, then it is a constant of the motion provided its Poisson bracket with the Hamiltonian vanishes or it Poisson commutes with the Hamiltonian. This is the reason why the Poisson bracket, among others, why the Poisson bracket plays a fundamental role in Hamiltonian systems. Now A could be one of the dynamical variables, the original dynamical variables themselves. What happens then? Then of course we have the following relations. We could compute the Poisson bracket of any qi with qj. This is easy to calculate and this vanishes as we have seen, and that is also pi with pj from our basic definition of the Poisson bracket. We also have qi with pj equal to the Kronecker delta ij, and that was the case in which we said a coordinate, generalized coordinate q and a generalized momentum p are canonically conjugate with each other provided that q with that corresponding p has a Poisson bracket which is equal to unity on the right hand side. These were the standard basic canonical Poisson bracket relations defining a Hamiltonian system. Now where does this get us? How do we go about solving for the Hamiltonian systems? How do we try to find the flow itself? One technique would be to use those constants of the motion which we can find by symmetries, and I will say a lot more about symmetries and constants of the motion a little later. One technique would be to find constants of the motion using the fact that you already have certain constants of the motion, and this is based on the Jacobi identity. Recall that this identity said that if you had three quantities A, B and C, then the Poisson bracket of A, B, C plus cyclic permutations is equal to 0. Two other cyclic permutations in which you have B with the Poisson bracket of C with A plus the third term equal to 0. Now suppose you discover that A and B are constants of the motion. So suppose A with H is 0 and B with H is also equal to 0. What does that imply? What would that imply using this fact? Instead of C, replace it with H. What happens to the Jacobi identity? Let us write this out explicitly, plus B with CA plus C with A, B equal to 0. Suppose instead of C I replace it with H and I tell you that A and B are constants of the motion, what would you conclude? This would identically vanish. So this Poisson bracket vanishes identically, so does that. And what does the third thing tell you? Exactly, so exactly, precisely. So this implies that H with the Poisson bracket of A with B is also 0. Therefore this quantity here is also a constant of the motion. This quantity could turn out to be trivial, it could turn out to be a constant, a numerical constant, it could turn out to be the identity function, it could turn out to be something utterly trivial, but there are cases where it could turn out to be a non-trivial function of the coordinates and the momenta, in which case having started with 2 constants of the motion we found one more. And in principle you could now find further commutators, further Poisson brackets and see whether you can find other constants of the motion. So that is one possible use of these Poisson brackets, to find other constants of the motion. But one should like to have a systematic way to integrate all the Hamiltonian equations at the same time. This is not a trivial task and in general is not doable. In general, generically it turns out that for Hamiltonian systems with an arbitrary number, say f or n degrees of freedom, you have basically only one constant of the motion available, namely the Hamiltonian itself, which implies that the motion can be extremely complicated. You do not really have much of a handle on it apart from knowing that for whatever initial conditions you start with, the motion is restricted to a 2n minus 1 dimensional energy surface, very little else can be said. But there are instances where the equations, the entire set of equations is integrable, and here is one way in which it happens. In fact it is the only way in which it happens. For this I must introduce the idea of canonical transformations. This is a mini subject in itself, but we are going to just get a small flavor of it here. So what I am going to say is restricted to certain special cases, but then we will see how far this kind of approach takes us. Okay. The idea is the following: suppose instead of starting with the coordinates and momenta q and p, I am able to find a change of variables, a change of dependent variables from the set qp to a new set of variables, and let us call those variables q comma p. There are n of these and n of these, so the total number of independent dynamical variables does not change, it is still 2n, but these new sets of variables, these new variables are functions of the old variables. And now let us suppose that this change of variables has a very special characteristic, namely the Jacobian matrix determinant, or rather of the change of variables qp is equal to +1. Suppose at all points where this change of variables is defined, these functions of the old variables and these functions of the old variables are such that this 2n by 2n determinant has the value +1 identically. What would you say happens to the volume element as written in the new variables? It would be the same. This would imply the flow is measure preserving. Volume elements remain unaltered. And suppose further that the change of variables is such that the following special property happens. The Poisson bracket of Qi with Qj is 0, as is the Poisson bracket of Pi with Pj, and further Qi with Pj is also equal to delta Ij. In other words, not only is the change of variables such that volume elements are unchanged, but the Poisson bracket structure is also unchanged. Suppose this is so, we are able to find such a change of variables. Notice that since this is +1 rather than -1, not only are volume elements unchanged, but orientations are preserved as well. So elementary parallelograms, if you define orientations for them, they would also be unchanged under this change of variables. One is then guaranteed, if this happens, one is then guaranteed that the structure of Hamilton's equations is also unchanged under this change of variables. This is not hard to show. Such transformations are called canonical transformations. I will abbreviate them by CT at various points. Together these properties imply that the structure of Hamilton's equations does not change. What does that mean? It means that if h of q comma p goes over to a new function when expressed in the new coordinates, which means this goes over to h of q, which is a function of the new variables, so the Hamiltonian when expressed in the new variables is obviously some other function of these new variables, let us call it k. Then we are guaranteed that under a canonical transformation if Qi dot is delta h over delta Pi and Pi dot is minus delta h over delta Qi, this implies that Qi dot is delta k over delta Pi and Pi dot minus delta k over delta Qi. So canonical transformations leave the structure of Hamilton's equations unchanged. In other words, it takes a Hamiltonian flow to another Hamiltonian flow in the new variables. The necessary and sufficient condition for this is that the transformation be canonical. In other words, that the Jacobian determinant be equal to +1 and the Poisson bracket, canonical Poisson bracket structure be unchanged. You are then guaranteed that these equations do not change in form, they are completely unchanged. Now you might ask, what is the use of this? Well, the answer is, it might turn out that you find a transformation of variables where some of the coordinates do not appear in this new Hamiltonian. If for example capital Q3 does not appear in K at all, it is not a function of capital Q3, then it immediately implies that P3 dot is 0 and therefore P3 is a constant of the motion. You have therefore found a constant of the motion, namely the momentum conjugate to the new coordinate Q3. If any new coordinate does not appear in K, it is called a cyclic coordinate or an ignorable coordinate, and the corresponding conjugate momentum is a constant of the motion. So let me write that down. New generalized coordinate Qj does not appear in K, then Pj dot is identically 0, Pj equal to a constant of the motion. And if it does not appear in K, then this coordinate is called a cyclic or ignorable coordinate. An extremely happy situation would be one if you found more and more cyclic coordinates, so that this set of equations can be integrated. The moment some particular new variable does not appear in K, a certain time derivative vanishes and you have discovered a constant of the motion. So one very happy situation would be if 2n minus 1 of these was 0, and then of course the matter becomes completely trivial, the vector field is rectified at once, only one derivative is non-zero and the rest are all 0. On the other hand, that is a very rare situation, hardly ever happens. More common is a situation where by a clever choice of variables n of these equations have 0 on the right hand side and only n of them have non-zero quantities on the right hand side. This tells you how such systems of equations are integrated completely in certain situations, and this is called a transformation to action angle variables, and we will talk a little bit about this to show you how Hamiltonian equations are integrated. We need a criterion for it, which I will state without proving here, and then we will apply that criterion to discover how to solve this set of problems completely, how to integrate these Hamiltonians. Again I point out that this is not the generic situation. Most Hamiltonians are not integrable in the sense that we do not have enough constants of the motion available to us other than the Hamiltonian itself, perhaps a few more. Right in the beginning I pointed out that in the Newtonian problem of a set of n particles interacting with each other by forces, by pairwise forces directed along the line joining any two particles, that system has, at least in non-relativistic mechanics, it has basically 10 constants of the motion, Galilean constants of the motion, whereas the phase space itself is 6n dimensional. This is the generic situation, the typical situation, but there are very, very important special cases where the set of equations can be integrated completely. Then of course the problem is solved in some sense. So we will take it from this point and try to understand how this magic happens and what the necessary and sufficient conditions for it are in order to integrate the entire set of equations. Here's, before I do that, here's a simple example of a canonical transformation which always works. Suppose Qi is just Pi and Pi is minus Qi. I simply call these by new labels. What happens to this? What is that equal to? Yeah, it is equal to minus Pi with Qj, but this is equal to plus delta Ij, because recall that the Poisson bracket of B with A is minus the Poisson bracket of A with B because of antisymmetry, and there is an extra minus sign. So this set of variables is canonical, they have the canonical Poisson bracket relations. And what happens to the determinant of the transformation? What is the determinant of this transformation in this case? So delta Q comma P over delta QP equal to this Jacobi determinant. What does that become? How do you find that? What is this matrix equal to? this is the determinant of a certain matrix, and what is that matrix? It clearly has zeros in the first block. What is in the next block? So this matrix here this thing here is the determinant of a certain matrix, and what is that matrix? It clearly has zeros everywhere here, and when you start writing those elements down, what do you get from this? Just the unit matrix. So just the unit matrix here, you get minus the unit matrix here and 0 here, and of course you recognize this matrix, it is J itself. So this is equal to determinant J equal to plus 1. Since it is an even dimensional matrix, its determinant, it is unimodular, the determinant is plus 1. Therefore this is a canonical transformation. Of course you do not gain anything much by it, but it helps you understand that this division of the variables into coordinates and momenta, while we started with mechanical examples where you can clearly distinguish between a coordinate and its conjugate momentum, that distinction from a mathematical point of view in Hamiltonian systems is quite artificial. There are two sets of variables, no question about it, but which ones you call the coordinates and which ones you call the momenta is largely irrelevant, because you have a canonical transformation which is guaranteed to let a Hamiltonian flow go into another Hamiltonian flow, in which it turns out that the original coordinates and momenta have simply exchanged roles with the appropriate minus sign there.
Does this new system have any physical relevance as well?
It is as valid a system as the earlier one, it is as valid. In other words, if you solve the original thing, you have solved this one too. So as it is, it does not mean anything, it does not tell you anything, but it gives you a certain symmetry of Hamiltonian systems which is going to be crucial in solving such Hamiltonian systems. So it is trying to tell you that this flow in this 2n dimensional phase space is a very special kind of flow. We saw that volume elements were preserved, many other things are preserved as well in this flow. And the natural language in which one writes this down is that of differential geometry, which we are not going to assume here, but let me say it in words so that you begin to see how constrained the Hamiltonian flow is. What is constant is the following: if this is a volume element in phase space, and let me draw it simply to fix our ideas as some kind of 3-dimensional object, in 2n dimensional phase space I have this volume element of initial conditions, and as time goes on this element flows in phase space like an incompressible fluid, might get distorted, squeezed out in certain directions, compressed in other directions, but the magnitude of this element does not change at all, the volume does not change, and I project this element, I project the shadow of this onto a particular QP space. So let us say this is Q1 P1, this plane, I project this volume element at any instant of time and I get a little shadow patch of this kind. I project it onto another plane which is the Q2 P2 plane, and let us say I get a shadow patch of this kind. I add up all these shadows, the areas of all these shadows, and that remains constant as a function of time. You are guaranteed that under a Hamiltonian flow the sum of projections remains constant. But what is the sum of projections? If this is the direction along Q and this is the direction along P, and this is delta Q, say Q1, and this is delta P1, then clearly this parallelogram has an area which is the magnitude of delta Q1 cross delta P1 regarded as vectors, this cross product, and you sum all these areas and the answer is guaranteed to remain constant. So schematically it says that under a Hamiltonian flow a summation from I equal to 1 to n delta Qi delta Pi, and this is a cross product in the sense of a parallelogram, the area of a parallelogram being written as a cross product of the two vectors defining the sides of it. That quantity is equal to a constant. This immediately implies that a certain quantity called a 4 form, but it is actually 4 differentials of this kind, 4 infinitesimals, also remains constant, and then something which involves 6 of these differentials, etc., till finally the entire product of all 2n delta q's and delta p's also remains constant, which is Liouville's theorem. So that theorem actually follows from the invariance under the flow of this area, this quantity here. One can show this rigorously using simple differential geometry, but I want you to appreciate the fact that the flow in phase space is what you have to think about, and it is a very special kind of flow. It has they are not constants of the motion in the sense of quantities which are dynamic, of functions of dynamical variables being constants of the motion. These are infinitesimals. So it says that this fluid element flows in such and such a manner, it flows such that all these magical properties happen for each fluid element. They are not constants of the motion in the sense of functions of all the q's and p's being invariant under the flow. Those are actual integrals of the motion. These are little infinitesimal differentials, and various combinations of them remain invariant, the last of which, there are n of these, and the last of this is in fact the volume element in phase space. So you could ask the converse question, given a flow in which these various differentials are constant, what kind of flow must it be? And the answer is it must be a Hamiltonian flow. In other words, the 2n dimensional vector field f is given by the symplectic gradient of some scalar function called the Hamiltonian of the flow. So there is a very rich and intricate mathematical structure associated with Hamiltonian flows. We do not have time to touch upon this, and it is outside the scope of this course, but it is important to remember that such a thing happens, that this exists. Let me come back to canonical transformations and point out what happens in a canonical transformation and why it is so important. And this goes under the name of integrability. Liouville-Arnold integrability of Hamiltonian systems, and the statement is the following. It says if there exist n constants of the motion, n COMs, f1 up to fn, that are functionally independent of each other, and that are in involution the phrase in involution implies that the Poisson bracket of any of two of these quantities is 0 identically. In other words, this implies fi Poisson bracket fj is identically 0, then the set of equations can be integrated. This is a loose way of stating the Liouville-Arnold criterion, but I will explain what this means term by term. So what is it really telling you? Recall that the flow is in 2n dimensional phase space. In order to integrate this set of equations and specify what the future values are given initial values, you need to have 2n minus 1 independent constants of the motion in a 2n dimensional space. The mutual intersection of these 2n minus 1 surfaces would in principle give you the phase trajectory for any given initial condition. But for Hamiltonian flows the following magic happens. The Liouville-Arnold criterion says you do not need to have 2n minus 1 constants of the motion. If you manage to find n of them, that suffices, but the catch is these n have to be compatible with each other in a certain sense, and that sense is that they must have vanishing Poisson brackets with each other, they must be in involution with each other. It's now we have to say what is meant by can be integrated. The answer is that this set of Hamilton's equations, explicit solutions to them can be written down in principle for all time. In other words, the full set of equations can be explicitly integrated, not numerically solved but explicitly integrated, and solutions can be written down in explicit form. This is what I mean by explicitly can be integrated. This of course is true in principle. In practice there are many slips between the cup and the lip, and we will see what the implication is, what is meant by these constants of the motion and how one goes about it.
Is this a more fundamental question?
Yes.
Is something like this more of a, if for example you are not able to integrate sin x by x, it's more of a limitation as of now, or is it a theoretical limitation?
The question is this a matter of, is this a theoretical limitation? Is this a constructionist kind of a constructive statement? In other words, is there some constructive way of finding these f's and doing the integration? What kind of statement is this? Well, right now when I make it, this statement says if there exist these constants of the motion, you are guaranteed that a solution exists for the problem. That is the level at which this statement is being made. It does not quite tell you how to find these constants of the motion, it does not also tell you having found them what do you do next, how do you go about integrating. The second question we will answer right away. The first question is much harder. What is the guarantee that a given system has or does not have these n constants of the motion? That has to be examined on a case by case basis. There is no general way of stating when a given Hamiltonian system is integrable. That is the first part. But now let me complete that. Having said that, I should also point out that the set of Hamiltonian systems for which this can be done is quite restricted, but it is a very important set, and the importance lies in the fact that for cases when it is not integrable, you can do perturbation theory, you can develop perturbative methods for answering questions of what happens to Hamiltonian systems where such a set of constants of the motion does not exist. Yeah, you.
For Hamiltonian system I have a set of 2n differential equations.
Yes.
Now if I am not able to find a solution, explicit solution for me,
yes,
for it, doesn't it mean that methods have not been developed till now? Like can you say on a theoretical note that.
Good question. So can we say that the problem is actually unsolvable in the sense that you can't? The answer is yes. This is a necessary and sufficient condition for the global integrability of Hamiltonian systems. So if you can't find these, or you can prove that such a system set of constants of the motion does not exist in a particular case, you are assured that it cannot be integrated for all initial conditions. So it works the other way too. This is a necessary and sufficient condition for integrability in the sense which we will elaborate upon. Yeah.
Can you give us a specific example where, like say this does not happen? I don't understand what you mean by not integrable.
Yes, we will come back to this, and I will give you examples where it is integrable. We will see specific examples where the system is integrable, and examples where you can't find these constants of motion, they do not exist, and therefore the problem is not, by this theorem, cannot be found as a global solution, cannot be found. We will come back to this, but we take this step by step. This is the first step. This is a necessary and sufficient condition. Now I have to explain what I mean by functionally independent of each other. We know that the Hamiltonian is always a constant of the motion, so the square of the Hamiltonian, or e to the power of the Hamiltonian, or the Hamiltonian cubed plus the Hamiltonian squared, they are all constants of the motion, but they are not functionally independent of h. these must really be independent of each other. In other words, none of them should be writable as some function of the rest, in which case they are completely functionally independent. The second point is there are certain technicalities here. What kind of constants of the motion are permitted? What kind of functions of the dynamical variables are permitted? As it stands here, these are assumed to be isolating integrals. They are supposed to be single valued functions, analytic in some sense. If they have singularities, then of course you again have problems, and then these theorems do not hold good in the form in which I have written them down. So subject to those caveats, which we will take up as we go along one by one, the first statement is, and this is what one has to pause and marvel at, that it is sufficient to know n constants of the motion and the entire set of equations is integrable in the following sense. What the theorem actually says is this can be integrated. This means there exists a canonical transformation, to a new set of variables for which the conventional notation is theta 1 up to theta n, I1 up to In. Recall we had said new variables, capital Q's and capital P's, but this very special set of variables which you have when the system is integrable are denoted by thetas and i's. These are called angle variables and these are called action variables. And it is a canonical transformation. So we are guaranteed that Poisson bracket relations are valid, we are guaranteed that the structure of Hamilton's equations is unchanged, such that the Hamiltonian H QP goes over to a new Hamiltonian which we denoted by K, which would have been a function of all the thetas and i's, but the magic is does not depend, the new Hamiltonian does not depend on any of the first n variables, the theta variables, depends only on the so called action variables which I have collectively denoted by I here. We are guaranteed this, that there exists such a set of transformations. Notice that since it is a canonical transformation, we also have the relations theta I with theta j is 0 is II with ij, and theta I with ij is delta ij, because it is a canonical transformation, and you are guaranteed that the structure of Hamilton's equations is unchanged. What does that imply? If this magic happens, then Hamilton's equations in the new variables become theta I dot is delta k over delta I sub I, and I dot equal to minus delta k over delta theta I for each I from 1 to n. But this function does not depend, by assertion we have already asserted that it does not depend on any of the angle variables, therefore these quantities vanish identically, all n of them, which imply immediately, which implies that II equal to constant of the motion for each I So we have trivially integrated n of the 2n differential equations of the Hamiltonian system, but we can go further. Once this is so, this is a function of all the action variables, and its partial derivative with respect to any one of them is also some function omega, let me call it omega sub I, of all the action variables which I collectively write as I. because this is a function of I alone, just the action variables, and its partial derivative is also a function of the action variables alone. But this is now a constant of the motion because the i's are constant for any given set of initial conditions, and it says the rate of change of any theta is a constant, which implies at once that theta I of t is the initial value, this, plus omega I, which is of course a function of all the action variables multiplied by t, and therefore you effected the actual explicit integration of all Hamilton's equations. All the 2n equations have been integrated out completely. Now let us take stock of this. What does this mean? Well, if that magic applies, if the Liouville-Arnold theorem applies, the criterion applies, and we are able to find these n constants of the motion in involution, then the assertion is that there exists a canonical transformation. Does not tell you how to find this canonical transformation, but you are assured that there exists such a transformation such that the new Hamiltonian has only dependence on the action variables and all the angle variables become cyclic coordinates, they are ignorable coordinates, which at once means that all the action variables are constants of the motion and the angle variables have a simple linear dependence on time. What determines the value of all these constants of the motion? The numerical values. What determines these numerical values? The initial conditions. You have 2n pieces of data, initial data, n of them go in determining these n constants and the remaining n go in determining the initial values of these angle variables. So what have we achieved? In the 2n plus 1 dimensional extended phase space, you need to have 2n constants of the motion to specify the motion, of which at least one must be time dependent so that there is motion as time goes on. N of them are these action variables, they are true integrals of the motion. The remaining are constants of integration, these quantities. This immediately implies that theta I minus omega I t is a set of n time dependent constants of the motion, which together with these first integrals, these i's, specify 2n, some of which are time dependent, 2n constants of the motion in the 2n plus 1 dimensional extended phase space, and the motion is totally determined in terms of these constants of the motion. So it is in this sense that the Liouville-Arnold criterion tells you the system is integrable, completely integrable. How do you find the original p's and q's once again? Remember, this was a canonical transformation with determinant equal to plus 1, the determinant is not 0, and therefore in principle the transformation is invertible. Given the thetas and the i's, I should be able to go back in principle to the p's and q's. They may themselves have very complicated motion dependencies on time, but the angle variables have very simple motion, very simple dependencies on time. You also begin to see that this kind of integrability is applicable in general to bounded motion in Hamiltonian systems, generally periodic motion or motion which is comprised of many characteristic frequencies which may or may not be commensurate with each other. So the motion may not be strictly periodic, but may be quasi periodic, just like if you took two simple harmonic oscillators at right angles, all of you are aware that if the frequency ratio of these two oscillators is a rational number, then the system comes back to its initial value, initial position, and the motion is truly periodic. On the other hand, if the frequency ratio is irrational, then the motion is not periodic in all the 4 dynamical variables, but only so in 2 of them at a time, the q1 and p1 and q2 and p2 separately, and you get these complicated Lissajous figures when you project this motion onto the q1 q2 plane. So in the same sense, this kind of integrability for bounded Hamiltonian motion implies that in general the motion is quasi periodic, with a characteristic set of frequencies which one might call the omegas themselves. But the important thing to note is that these omegas depend on these constants of the motion, and therefore if you have different constants, if you start with different initial conditions, then in general the characteristic frequencies of the system also change. This is a feature which is not present in the harmonic oscillator or linear problems of this kind, where the frequencies are given to you right in the beginning. Here the frequencies are energy dependent, they are initial condition dependent in general, but the motion is solved, it is completely solved for. Now you could ask, is it so that these i's are the f1, f2, fn's themselves? Is that true? The answer is, after all they are in involution with each other as well. The answer is, in general these action variables are not the constants of the motion f1 through fn themselves, but they can be constructed from them. You can construct from these constants f1 through fn, you can construct appropriate action variables which would then be canonical variables in the sense that those Poisson bracket relations are valid. That is the crucial point. This thing has to be valid here. Now let us point out one final thing. What is the meaning of having two functions in involution with each other? What does this imply? And this matrix J we talked about gives us a very simple way of understanding this geometrically. In fact, most of Hamiltonian mechanics is something called symplectic geometry. It is understandable in geometrical terms in phase space. We already saw that the flow itself was always along the level surface h equal to constant. Suppose I take two quantities A and B and take their Poisson bracket and ask, can I write that in compact form? And the answer is yes, and it is done in a very revealing form. So if A Poisson bracket B equal to 0, this of course means that summation I equal to 1 to n delta A over delta Qi delta B over delta Pi minus delta A over delta Pi delta B over delta Qi is 0. This is what it implies. Using this matrix J, we can write this in an extremely simple form. This quantity is also equal to, clearly certain derivatives are acting on B. So this is also equal to the gradient of B in phase space with these 2n derivatives delta over delta q1 up to delta over delta pn. This thing is a certain vector and can be written as a column vector, delta B over delta q1 all the way down to delta B over delta pn. This vector with a j here and the gradient of A here with a transpose to show that this is a row vector, delta A over delta q1 horizontally all the way up to delta A over delta pn. The transpose of this is a row vector here times the J matrix times delta B, and that is what the Poisson bracket is. So it says this is equal to 0 if the Poisson bracket vanishes. So it is as if the gradient of A and the gradient of B are not quite normal to each other, which is what would happen if the dot product vanished, but in a symplectic sense they are normal to each other, because once you put the J in between here, this is 0. So what does that tell us? Whenever you have a constant of the motion, it implies that the motion is on the level surface of this function, because we saw that a constant of the motion implied that it does not change as the flow occurs. And now in addition to the level surface of the Hamiltonian, if you have other constants of the motion, then the flow is on the level surfaces of both these flows. And the fact that this dot product, pseudo dot product vanishes implies that these vector fields, gradient of A, gradient of B and so on, are in some sense independent of each other, they are linearly independent of each other. So we really have a mathematical structure for Hamiltonian flows if the Liouville-Arnold criterion is satisfied, which says that these n quantities, gradient f1, gradient f2 dot gradient fn, of which the first could be chosen to be the Hamiltonian itself. So this is delta H. These n vector fields form a kind of basis on the surface on which the flow actually happens. That restricts the kind of surface you could have. So a very special thing happens once this magic of integrability occurs, and in some sense the flow is reduced from a 2n minus 1 dimensional energy surface to an n dimensional object in the action angle variable space. That n dimensional object is the generalization of a torus, it is an n torus, and we will see why this comes about, and we will also see why these are called angle variables and what the significance of action variables is. And this will also help us explain a mystery which you might have come across when you did elementary quantum mechanics, when you are told that integral p dq equal to n times Planck's constant, and this was the Bohr quantization rule. This will help us get a handle on why that happened, why this thing happened. And incidentally, Planck's constant has the physical dimensions of action, which is energy multiplied by time, and that is exactly what the reason why these are called action variables, and it is action that is quantized in Planck's constant in Bohr quantization, in the original quantization. So we also have a connection with semi-classical quantization at the same time, and all this follows from the structure of integrable Hamiltonian systems. So we will come back to this, and I will get back here and explain what canonical transformations do, what these transformations mean really, what kind of system, what kind of geometry is implied by these transformations, and then we will look at special examples of various cases, including some problems we know how to solve already, like harmonic oscillators and collections of oscillators, because the lessons we learned there are generalizable to more difficult cases. This is what we will take up next. Okay, we continue with Hamiltonian dynamics from where we left off. Recall the conditions we had for the integrability of a Hamiltonian system. Once again, given a Hamiltonian Q comma P with f degrees of freedom, I think I used n degrees of freedom, we have Hamilton's equations. Qi dot is delta H over delta Pi, and Pi dot is minus delta H over delta Qi for I running from 1 to n. And I pointed out that this system is integrable in the sense that you can explicitly write down time dependent solutions for all the Q's and all the P's given any set of initial conditions, provided there exist n constants of the motion f1 to fn in involution with each other, such that the Poisson bracket of any fi with any other fj vanished identically. If there exist these constants of the motion, then the system is integrable and the problem is completely solved. And it was done by going to what are called action angle variables, where the Hamiltonian H of Q comma P was transformed by a canonical transformation, a transformation with Jacobian equal to +1 and the Poisson bracket structure preserved, to a new Hamiltonian in variables called action angle variables, and this became a function of just the action variables. And then one discovered that the problem was completely integrable, completely solvable. Now what does this imply in geometrical terms? This is what we were trying to understand, and I pointed out that the Poisson bracket condition, this quantity vanishing here, can be rewritten in terms of this matrix J we introduced, which was a 2n by 2n matrix with zeros here, the unit n by n matrix here minus the unit n by n matrix here, and this condition simply became this quantity equal to the gradient of Fi transpose J, the gradient of Fj. In other words, these vector fields formed by the gradients of these constants of the motion of these functions of q's and p's, they are pseudo orthogonal to each other in the sense that the dot product of this row vector with that column vector is 0. This means that if the system is integrable in the Liouville-Arnold sense, there exist n vector fields formed by the gradients grad f1, grad f2 through grad fn, which are independent of each other on the space of these i's and thetas completely. That has a profound implication, and it implies that you have in this 2n dimensional phase space a 2n minus 1 dimensional energy hypersurface. The motion is restricted to that for any set of initial conditions. Over and above that, the motion is actually restricted to a subspace of this 2n minus 1 dimensional energy space, such that these n quantities are constants completely. Moreover, on this n dimensional subspace, the n vector fields formed by these gradients are independent of each other. Now it turns out that there is a deep theorem mathematics which says that if you have a space which is compact and everywhere in this space you have n independent vector fields, by compact I mean it does not go off to infinity, it is unbounded, there is a technical definition which we will write down a little later, then the only such space possible is isomorphic to something called an n dimensional torus, and let me explain that in slow terms. A one dimensional space which is compact and which has at every point a unique tangent vector would be something like a circle, and the mathematicians would denote this by S1. This space is one dimensional, and at every point on this space there is a unique tangent vector, a straight line which runs from minus infinity to infinity tangent to this point, and as you can see, if you took this tangent and moved it along this entire circle, when you come back here you come right back to the same point, to the same tangent as before. Such a space is said to be parallelizable or developable in the sense that you can unroll it, you can roll it on a sheet of paper and make a one-to-one mapping between a straight line segment and this circle without any kinks, without any difficulty at all. You can do exactly the same thing with a two-dimensional donut, a torus, in which you can take two vector fields, one of which is for example directed along these lines and the other one is directed along these lines, this direction, form a basis from these two vector fields and move it all over this space and come right back to the starting point, to the original configuration itself. You can't do that on a sphere. This is by the way called the direct product of two circles, it is just the Cartesian product of two circles, and it is called the two torus. A moment's thought shows you that you can't do this with another two-dimensional object, the surface of a sphere embedded in 3 dimensions denoted by S2. It is not possible to find a unique tangent map which is not singular at any point on this sphere, because if I start with some point here and draw the tangent plane to that point, as I move it around it is clear that there is going to be at least one point where this direction of this tangent plane is undetermined there is a singularity. What does it mean? You could define this tangent plane by saying, imagine like a tennis ball, that there are fibers sticking out of this ball and you are trying to comb it, and when you comb it, it is clear that somewhere, maybe at the north pole, there is a little cowlick, there is a little point that sticks out, a singularity of the vector field. So the technical way of saying it is that there is no non-singular global tangent map to S2 like there is to S1 or T2, and the statement being made here is that the most general space which is compact and which is parallelizable in the sense that you can form a basis set of n vector fields.
Could you explain why there should be a singularity?
Pardon me, could I explain why? This, imagine combing a ball, imagine combing a tennis ball, what happens? You comb it down everywhere, flat, tangent. What happens? Can you do this without a cowlick, without a parting? There is at least one point where there is going to be a singularity and the hair sticks out, the direction in which it is placed is indeterminate, there is a singularity of this field, there will be a bald spot invariably. That is not true for a torus, you can comb it down completely. So this is a basic difference in a property of a torus as opposed to a sphere, and the statement being made here is that if you can find n independent vector fields on an n dimensional manifold which is globally applicable, smooth everywhere, then that space has to be an n dimensional torus. It is a generalization of the 2-dimensional torus. I cannot draw an n dimensional torus here because I cannot draw anything more than 3-dimensional. Where it applies here is the fact that integrable Hamiltonian systems, integrable in the sense of Liouville-Arnold, the phase space on which the action takes place is eventually just n dimensional, not 2n dimensional. It is reduced from 2n to 2n minus 1 by the constancy of the Hamiltonian itself. Now it is further reduced from 2n minus 1 to just n by the fact that it is integrable. Now this is an abstract statement, we will look at specific examples and see how this works out. So we take simple examples and I will take the simplest of them all, namely the harmonic oscillator, and we see how this thing comes out, how the 2 torus structure comes out for a couple of uncoupled, for a pair of uncoupled harmonic oscillators. So we will do that step by step, and before I do that, let us give a few examples of what Hamiltonian systems look like. So this was a bit of a digression, but we come back. So first let us look at the linear harmonic oscillator. This is of course our simplest problem of all. It has got 1 degree of freedom. The Hamiltonian as a function of a single q and a p is 1/2, it is p squared over 2m, the kinetic energy plus the potential energy V of q, which in this case is p squared over 2m plus 1/2 m omega squared q squared, where omega is the natural frequency of the oscillator and m is its mass. Of course we are going to get equations of motion which are just the simple harmonic oscillator equations of motion, but let us go through the steps simply to see how this works out, and we know that q dot is delta h over delta p, which turns out to be just p over m in this problem, and p dot is minus delta h over delta q, that is equal to minus m omega squared q. We have just written Newton's equations down because the conventional Newton's equation would say q double dot, the acceleration, is equal to 1 over m times the force, which would be the rate of change of the momentum. So together it is clear that this implies the usual q double dot plus omega squared q equal to 0. which is the oscillator equation of motion. But like I said, we prefer to write everything down in phase space because that is where the dynamics is taking place, and we have this set of coupled equations. Now let us go through the formal analysis of this. This is a linear set of equations on the right hand side, so there is no need to linearize the problem, it is already linear. Where is the critical point of the system? At the origin, the right hand sides must vanish, so the only critical point is at 0, 0 in the QP plane. What about the matrix L which acts on the right hand side? It is 0, 1 over m minus m omega squared and 0, and what are the eigenvalues of this matrix? Plus or minus I omega. So it immediately says lambda 1 comma 2 is plus or minus I omega. This implies 0 comma 0 is a center. Is that stable, unstable, or asymptotically stable? It is stable, it is not asymptotically stable, it is just a stable center. And what do the phase trajectories look like? In general they are ellipses depending on the units you choose, because there is just a single constant of the motion in this problem. Since n is 1, the set f1 through fn becomes just f1, and you need to find just one constant of the motion to integrate the system. That constant of the motion is already given to you, it is the Hamiltonian. Remember that for any Hamiltonian system which is autonomous, the Hamiltonian is always a constant of the motion. So we have a phase portrait in this case which is just a set of ellipses h of qp equal to a constant, and in this case the constant is simply the total energy of the system. In which direction is the phase trajectory traversed? Would this be in the counterclockwise or clockwise direction? Why do you say that? Exactly, if you pull this oscillator and let go from the rightmost point, it moves back towards the left, so P becomes negative at that point, and therefore if you start here, the next instant it is here, and that fixes the direction in which this thing is traversed, therefore clockwise. The critical point at the center, at the origin, is a stable center. All motion is periodic no matter what the initial conditions are, and every point in this plane lies on one and only one ellipse. Phase trajectories do not intersect themselves for autonomous systems, and the entire plane is laminated by these concentric ellipses. What is the time period of motion? It is 2 pi over omega, and it happens to be independent of the energy in this problem. Because it is a linear harmonic oscillator, it turns out that this is one of the unique properties of the harmonic oscillator, that the time period is independent of the amplitude of motion or of the energy of the motion. There are other oscillators which are not linear, the equations of motion of which are not linear, for which this phenomenon occurs, and we will come up with an example very shortly, a little later, but this is a distinguishing feature of harmonic oscillators, unless of course you look at a very special class of oscillators which are nonlinear but also isochronous. Anything where the time period is independent of the energy is called isochronous. So in this problem, the motion does occur, as you can see, on one dimensional tori, on a torus which is essentially one dimensional, namely this curve itself, or on this curve. And this magic happened simply because this problem had a potential which was quadratic, and therefore it led to an equation of motion which was linear on the right hand side. So the problem is exceedingly simple, as you can see. Now let us take this a little more general, again with 1 degree of freedom, and see what we can say before we go on to 2 degrees of freedom. Suppose I have a general potential of this kind, what would this equation of motion become on this side? Yes, just the derivative, minus dvq over dq, and of course that is the force minus the gradient of the potential with respect to the coordinate. So we recovered Newton's equations of motion, except that now the critical points of the system would be given by the vanishing of P and the vanishing of V prime of Q, in other words the extrema of the potential. These could be maxima, these could be minima, they could be inflection points at which the slope is 0. And then of course you would have to further examine the stability or otherwise of these critical points. And you could in principle write the entire phase trajectory down, the phase portrait down, simply because there is just one constant of the motion. But notice one interesting fact right away. So let us say where the Cp is located at p equal to 0 and the roots of V prime of Q equal to 0, which correspond, as we have said, to just the extrema of the potential. But notice an interesting fact right away, that the phase trajectories are actually already known to you. They are simply given by p squared over 2m plus V of Q equal to constant. Since one equation between two variables p and q on a plane specifies a curve, the phase trajectories are completely specified even without solving the equations of motion. Solving the equations of motion for a specific set of initial conditions will of course tell you how p and q change as a function of time explicitly, but to write the phase trajectories down you do not need that. Notice something else, notice also that the phase curves are given by dividing this by this equation, and you get dp over dq is equal to minus V prime of Q divided by p, m times that. Therefore, whenever the phase trajectory intersects the horizontal axis, the q axis, it will generally do so at right angles, because this quantity vanishes on the x axis, on the q axis, but this may not. If it does, then you have to examine the problem further and take limits, but otherwise phase trajectories would intersect the q axis at right angles, and that is indeed what happened in the harmonic oscillator example, where you had this kind of behavior and these were at right angles. That happened because the restoring force is not 0 at those turning points, at the end points of the motion, but the momentum vanished at those points. You could integrate this equation, you get p dp plus m V prime of Q dq equal to 0, and if you integrated it, what would you get? You would simply get p squared over 2m plus V of Q equal to constant, which we already know. So in principle a 1 degree of freedom Hamiltonian system is always integrable, you do not need any further conditions. Let us look at a potential which is a little more complicated than a linear one. So let us suppose V of Q, and let us choose units conveniently so that I do not have to run into problems with writing these constants down. So let us simply write p squared over 2 plus perhaps q squared over 2, so it is a harmonic oscillator without any extra terms, but then I include a nonlinearity and make it q cubed over 3 in suitable units. What happens to the right hand side here? This becomes p, and what happens here? Minus q, because you need a minus sign there, minus q squared. that becomes equal to minus q times q plus 1. Where are the critical points of this system? Well, 0 0 is still a critical point, but minus 1 0 is also a critical point, and we can easily write down what the solutions are. 0 0 and minus 1 0. We should draw the phase trajectory or phase portrait, but before we do that, let us draw the potential so we get some physical idea of what it looks like. So here is the q axis, here is V of q. Now what does this potential look like? Just this alone. Sufficiently close to the origin, the q squared dominates over the q cubed, and therefore it looks like a parabola. So we certainly guaranteed that the potential looks like this here, and then for large positive q it shoots off like q cubed, goes off to infinity. But then for large negative q, this term dominates over this no matter how large you get. Once q becomes sufficiently large, this becomes much bigger than this, and then this curve has to come down in this fashion. And not surprisingly, this extremum is at minus 1, this is at 0, which is a minimum there, and a maximum at minus 1. What do the phase trajectories then look like? So if you permit me to draw it on the same curve, on the same vertical axis, but now I draw P here versus Q, this would be a critical point and this point here would be a critical point. And it is quite apparent that this is a center about which you have stable oscillations, small oscillations, and what kind of critical point would this be? It would certainly be unstable. You would have to linearize the equations of motion about the point q equal to minus 1. So you might want to set, say, u equal to q plus 1 and then shift the origin to q equal to minus 1 and see what happens in the vicinity of this point. But we have already seen that for Hamiltonian systems there is no dissipation, and the only critical points possible are centers and saddle points, and this is a saddle point, it is unstable, and that is a center and that is stable. What do the phase trajectories look like? What would the phase portrait look like in this problem? You would have to specify now the initial conditions. In other words, you have to tell me the initial q and p, or better still, tell me the initial value of the energy, and that remains constant because you are on curves in which this quantity is constant. So what we are really doing is plotting the curve p squared over 2 plus q squared over 2 plus q cubed over 3 equal to a constant. That constant could be positive or negative in this problem because this term could take on large negative values as well. So what would these phase trajectories look like in general? Suppose I started with a value of the total energy that corresponded to some level like this, at this level on this figure. This is the 0 of the energy of V of q. Suppose I had a total energy equal to this much. Where would the motion be? This is my total available energy. It is clear I can't go into this region because if I did so, then this quantity V of q plus p squared should be equal to this number, but V of q is already larger than this number, which implies p squared should be negative. That is not possible with real p. So if this is the total energy, the system does not have enough energy to get into this region, it is restricted to this region, and therefore it can never move to the right of this point. Now imagine you start with a little ball bearing here in this potential hill and let go from rest. What would it do? It would move away to q equal to minus infinity with increasing acceleration. In which direction would this acceleration be? To the left or to the right? In which direction would the momentum be? It would be to the left. it would move further and further to the left. So P would get more and more negative and Q would get more and more negative, and therefore this is what the trajectory would look like. On the other hand, imagine starting at minus infinity in Q and shooting a ball up this potential hill with a fixed amount of energy equal to this much. It is clear it can crawl up this hill, this barrier, up to this point where its energy, where its kinetic energy goes to 0, and then it rolls back. What would that trajectory look like, that half trajectory, where it starts there and moves to the right, but with smaller and smaller values of P, of momentum, till it reaches this point with 0 momentum. It would therefore be the other half of this curve. And in principle, if you shot something here, you started off with something here with this much total energy at minus infinity, it would crawl up this hill and fall down corresponding to this phase trajectory. And as we know already, since the restoring force at this point is not 0, the slope is not 0 there, V prime of Q is non-zero at that point, therefore it must intersect this line at right angles. What happens if I have a little higher energy? Nothing much happens, it follows another trajectory which does this. What happens if I have a total energy equal to this much? It is clear that the particle could move up to this point and this would be a trajectory, but it is also clear that if the initial conditions permitted it to be inside this region to start with, it would simply oscillate about that origin. Therefore, for the same value of the total energy, there exists another trajectory which would correspond to oscillations. As I said, a closed phase trajectory implies periodic motion and vice versa. So for the same total energy, there are two regions in configuration space where the particle could find itself. One would be to the left of this point and the other would be in this well. Motion here would correspond to periodic motion, motion here would correspond to open or unbounded motion. But both these phase trajectories correspond to the same total energy, same value of H equal to constant, same constant. These oscillations here would, for sufficiently small energies above 0, be essentially ellipses, because you could neglect the effect of the Q cube term and then you have a harmonic oscillator. But it is quite evident that as the amplitude increases, this is no longer a parabola but it flattens out on this side and becomes cubic on that side, and therefore it is non-harmonic. It is some kind of oval, but it is still periodic motion. The time period in general would depend on the energy, except for very, very small amplitude oscillations when the system looks like a simple harmonic oscillator. What happens if you have an energy which is higher than the height of this barrier? It is clear that the barrier no longer can trap this particle into oscillatory motion, therefore this would be open trajectory of some kind, an open trajectory. Imagine shooting the particle up, it comes up here, it certainly slows down because you have very high potential energy here, but then it crosses this barrier, falls into this well, climbs up till that point and then goes right back and falls off in this fashion. Therefore I would expect this thing to come down, to go round and go off, escape to infinity, again crossing this at right angles. That is what would correspond to an energy which is higher than the height of the barrier. So now you begin to see that there is one very special value of the energy where these two possibilities, namely periodic open motion versus periodic motion, they merge, the boundary between the two, which would correspond to a total value of the energy a value of the total energy which is exactly equal, let me call that E sub s, which would correspond to two different kinds of motion. One of which would be, remember this point by itself, this point by itself is an unstable critical point, it is a phase trajectory by itself. If therefore you shoot a particle from here up this hill with just this critical value of energy so that it can barely reach it out there, it is going to take an infinite amount of time to do so. It would eventually, as t tends to plus infinity, go and stop there in this fashion. That would correspond to a trajectory which comes along like this and tends to this point as t tends to plus infinity. Had we started with a particle there and displaced it infinitesimally to the left, it would fall off and go off to minus infinity here, which would correspond to this. Had we started on this side up here and pushed it slightly to the right, it would go up the barrier, go down this well, go up to this point, turn back and come back and crawl back to this point. And the reason it would crawl back is because the slope is getting flatter and flatter, the restoring force is getting smaller and smaller, and therefore it is barely able to reach this top. It would therefore do the following, go here, go around and come back, and this point of course would correspond to that. So it is quite clear that a lot of interesting things happen in this region, and let us magnify that region and see what it looks like. That region near the separatrix, there is a saddle point here, there is an unstable orbit coming out of it which eventually falls back, tends back towards it, and then there is a separatrix which is flowing in and something which is flowing out. I should really let these things tend to that point asymptotically, but instead of that let me just draw it in this fashion so you can see that this is a limiting point. This saddle point, if you linearized about the saddle point, you would discover that the system has two eigenvalues, one of which is positive and the other is negative, and the two eigendirections or eigenvectors of the linearized matrix L would correspond to these directions. This is called the stable manifold of this critical point, and that is called the unstable manifold of this critical point. And as is typical of a saddle point, two lines come in and two lines go out. Near this saddle point the system is hyperbolic and the whole thing looks like hyperbolas, the phase trajectories look like hyperbolas, so you have behavior of this kind. Of course these trajectories would eventually flow off and this would go around and join up there, and similarly inside here these would be parts of periodic orbits and these would be parts of open orbits, but locally it looks like a saddle point should. Notice also that this tangency here is not at right angles. This is the one case where this intersection at right angles does not happen, and the reason is V prime of q also vanishes at this point, and therefore you have to take the limit V prime of q over p as you approach the critical point. Both numerator and denominator vanish at that point, and you have this typical saddle structure. I leave it to you as an exercise to find out in this problem what this angle is, what the angle subtended by the two separatrices are. This trajectory which separates open motion of this kind from open motion of this kind is called a separatrix. Corresponding to the energy E sub s, and that is the reason I used a subscript s there to show that it is energy corresponding to a separatrix. This trajectory is a separatrix. and this trajectory which separates open motion from periodic motion inside this closed loop is also part of the same separatrix. This particular trajectory has an even greater significance. There is a special name given to it because it is starting off from a saddle point, moves off in the unstable part of the unstable manifold, and it loops back and comes back to the same saddle point as part of the stable manifold. Such an orbit is called a homoclinic homoclinic orbits play a crucial role in the behavior of nonlinear dynamical systems. As you can see, small changes in initial conditions around these separatrices around this point can cause very different futures altogether. This is a lesson of some generality. If I started here slightly above the separatrix, I would move down this way and move off there, but if I started here I move off somewhere else. Similarly, if I am here I move off altogether to infinity, but if I am here just inside this loop I keep going around. So it is clear that separatrices play a very crucial role in the behavior of nonlinear systems. This is a nonlinear system, it is very clear. Because of this the equation of motion has become nonlinear here, and that is responsible for many of the things that we see here. Having seen what a typical phase portrait would look like for such a one dimensional problem, a simple problem, let us look at the very model of one dimensional problems of this kind, the simple pendulum in the absence of dissipation. And once we do that we are set to look at higher degrees of freedom. What I mean by a simple pendulum is a mathematical pendulum. It corresponds to a bob of some mass m suspended without friction from by a light rod of some length L. So this is the point of suspension which I take to be the origin, and from that you have a light massless rod of length L and a heavy bob of mass m. And the motion of this pendulum is in a specified plane, say the plane of the blackboard, and the angular displacement about the vertical I call theta, and the pendulum moves back and forth in this fashion. Now the question is, what sort of Hamiltonian does it have? Once again, because we know there is no friction in this problem, the degree of freedom that we have is 1. The dynamical variable which specifies the position of the pendulum at any point at any time is in fact the angular coordinate theta about the vertical. So it is a function of theta and a conjugate momentum p theta, which is nothing but the angular momentum of this pendulum, the orbital angular momentum of this bob about the origin, and this is p theta squared twice ml squared. Since ml squared is the moment of inertia of this bob about the origin, so it is the square of the angular momentum divided by twice, I am sorry, should have switched it off earlier. So it is the square of the angular momentum divided by twice the moment of inertia plus the potential energy, which is a function of the angular displacement theta alone. Now let us assume that the potential energy is 0 when the bob is at its lowest position. Then when it is at an angle theta about the vertical, the potential energy corresponds to raising the bob by this height here, and therefore it is nothing but twice ml squared plus mgl times 1 minus cos theta. So you have to subtract this distance from that distance multiplied by mg, and that gives you the potential energy. Now remember, this is a light massless rod, a rigid rod, and therefore two kinds of motion are possible. Either the pendulum oscillates about its lowest point, or else it rotates completely, and both possibilities are included in this expression for the potential energy. So all we have to do is to plot this potential energy, find out where the maxima and minima of the potential are, and we have our phased portrait. So let us do that. Let us write down what V of theta looks like. We have to plot mgl times 1 minus cos theta, and that is simple. It has a bunch of maxima and minima of this. This is at 0, this is at minus 2 pi, this is at plus 2 pi, and so on. This is at pi, this is at minus pi, this is at minus 3 pi, and so on. Where are the critical points of this system? Well, let us write the equations of motion down. Then of course, theta dot is delta h over delta p theta, which is equal to p theta over ml squared. Just corroborates the fact that the angular momentum is the moment of inertia multiplied by the angular velocity, theta dot. The dynamics is buried here, p theta dot equal to minus delta h over delta theta. What is that equal to? It is equal to minus mgl sin theta. I differentiate this, I get a minus sin theta. This minus goes against this minus and cancels. Is this a linear system or a nonlinear system? Highly nonlinear because of this sin theta. It has got all powers of theta in it, all odd powers. Of course you can eliminate p theta completely by differentiating this a second time and substituting for p theta dot here. And what would you get? You get theta double dot plus g over L sin theta equal to 0. That is the famous pendulum equation. And if I call g over L this quantity the square of the natural frequency for small oscillations, then this simply says, or theta double dot plus omega naught squared sin theta equal to 0, where I have set omega naught squared equal to g over L. This equation is very famous, there is a long history, it is a nonlinear second order ordinary differential equation, it is called the sine Gordon. For reasons we will not go into right here, this started off, this name was a joke to start with, but then it stuck completely. It is similar in form to an equation which is known in other contexts, for instance in relativistic quantum mechanics, called the Klein-Gordon equation, and this nonlinear equation is related to the Klein-Gordon equation, and because it has a sign here it was as a joke initially called the sine Gordon equation, and that name has stuck completely. It has got a long and distinguished history, very interesting properties. It is a very nonlinear equation, but it has some very special solutions, as we will see. Nonlinear because of all powers of theta sitting here. I might mention here that you can actually solve this equation in general, and the solution is in terms of elliptic functions and elliptic integrals, which are not elementary functions, they are not ordinary trigonometric functions, they are a little more complicated than that, but we are not going to do that, we are not going to write the solution down, we are going to look at the phase trajectories and see what the phase portrait looks like. I remind you that in the small amplitude approximation where you can replace sin theta by theta, this becomes the harmonic oscillator equation, and then of course the time period of oscillation is just 2 pi over omega naught. But that is only true for small oscillations. The moment the oscillations become reasonably large in amplitude, then the time period depends on the amplitude and in fact increases with the amplitude in a fairly complicated fashion. Now what do the phase trajectories look like? Where are the critical points? So CP's at p theta equal to 0 and theta equal to the zeros of sin theta, which happens at all integer multiples of pi. Now of course, to cut a long story short, we pretty much know what these critical points are going to be like. So if I plot p theta here versus theta, I know that this is a minimum of the potential and therefore there is a center here. So is this, there is a center here, and so is this, there are centers here, these points. So centers occur at all at 0 and all even multiples of pi. What sort of critical points do you have at odd multiples? They are maxima of the potential, they are unstable, and in this Hamiltonian system the only possibility is saddle points once again. So you have a saddle point here, a saddle point at this point, a saddle point here, a saddle point here, and so on. What would the phase trajectories look like? Well, it is quite clear that in this problem the only allowed values of the energy are non-negative of the total energy. The moment you have a small positive energy, the system could find itself trapped in either this well or this well or this well or this well, and in each of those it would execute small oscillations looking like that, a little higher energy, and these oscillations would have slightly bigger ovals. These are not ellipses except for extremely small amplitude oscillations, because this theta is not approximated, this sin theta is not approximated by theta except for theta sufficiently small, sufficiently close to a even multiple of 2 pi. And then of course these are ellipses as you come closer and closer, but after that they are ovals given by this quantity equal to a constant, the entire Hamiltonian equal to some constant. What would happen if the energy were larger than the maximum value here, and the maximum of the potential, this thing here, corresponds to, by the way all these maxima are at exactly the same point, same value, this maximum corresponds to the separatrix energy, which is twice mgl, because that corresponds to theta equal to pi, in which case the potential energy becomes twice mgl. So if E is greater than twice mgl, I would expect the motion becomes unbounded, because instead of oscillating this way the amplitude keeps increasing and finally it has got enough energy to overcome the barrier and go all the way around, and then it would be open motion, it would go this way or the other way, and this would correspond to open trajectories right here or here. But the interesting thing happens when you have an energy equal to the separatrix energy. Then of course you could, for example, start here at minus pi, crawl down extremely slowly, accelerate as you come down, and go up and crawl up all the way to plus pi. That would correspond to a trajectory which starts here and ends there, and vice versa, which would correspond to something doing this asymptotically. Similarly, you could start here and go there, which would correspond to a loop like that. So now you have saddle points in which this is the unstable manifold and this is the stable manifold, the tangents there if you linearize about these points, but now you have a situation where these loops go from one saddle point to the other and back from the next back to this. Such a loop is called a heteroclinic orbit. and of course they correspond to, on this trajectory the energy is E sub s. And what about the open trajectories? It is clear that you would have an infinite family of open trajectories which would look like this, and on the other side etc. And as the energy increases, these things would get flatter and flatter. So such a trajectory would correspond to counterclockwise rotation, in which theta is going on increasing monotonically, and the other one corresponds to clockwise rotation, where theta becomes more and more negative monotonically. The separatrix, as before, separates rotational motion from oscillatory motion. The interesting point, and that is it, this is the phase diagram of the undamped simple pendulum. The moment you put in damping, the moment you have a first order term here, a theta dot term, which would correspond to a system which is not Hamiltonian, then this entire picture changes, and it is clear no matter where you start, maybe it rotates a few times, but eventually it comes to a halt, it would oscillate and then damp out. So the trajectories would look very different altogether, and the fate of any point on the phase plane wherever you start would depend on where you started, which of these it gets attracted to, because all these points would become stable spiral points, asymptotically stable spiral points, and which one it goes to depends on where you start. What is interesting is that for very small amplitude oscillations the solutions are trigonometric functions. The general solution of an equation with the theta here is simply cos or sin omega naught t. The solutions for larger amplitude oscillations are elliptic integrals, as I mentioned, but the solution for this critical value of the energy on the separatrix is again expressible in terms of elementary functions. Once again it turns out that you do not need any elliptic integrals or anything like that. If you set the total energy to be equal to twice mgl, then those trajectories are actually simple to write down, and the reason is on those trajectories I would have h of p theta and theta equal to p theta squared over 2 ml squared plus mgl times 1 minus cos theta equal to twice mgl. This is true. And of course we know what this term is, it is nothing but 1/2 ml squared theta dot squared, and if I bring that down to this side or take this over to the other side, what happens? Comes 1 plus cos theta on the other side, the m gets removed, we take the 2 there, and the right hand side gets simplified. What is this equal to? This is twice cos squared, so this becomes 4g over L cos squared theta over 2. If you took this trajectory for example, in which theta dot is positive, then corresponding to that you have theta dot equal to twice root g over L cos theta over 2. So on that trajectory theta dot equal to twice square root of g over L, but that is omega naught cos theta over 2, and this can be integrated, because all you have to do is to rewrite this as d theta times sec theta over 2 and integrate it, and it can be done in terms of elementary functions. So I leave it to you to write down the explicit solution for an initial condition where at t equal to 0 you are at theta equal to 0, and as t tends to plus infinity you are going to approach theta equal to pi, and at t equal to minus infinity you would start off from here at this point. So I leave you to write this solution down and then we look at its special features. And once we are done with this, we can move on to understanding how 2-dimensional and higher degrees of freedom integrable systems would lead to the torus structure I mentioned earlier. So we will do that next time. Any questions? Yeah.
Actually, a phase trajectory is a graph of the positions in phase space with time, right?
It's not with respect to time. Time has been eliminated completely. So the reason you draw an arrow on phase trajectories is to tell you in which direction the phase space point, the representative point representing the system, moves as time increases. Yes. But time itself does not appear here. It is clear that time has gone, has been eliminated, and what you have done is simply to say where does the point which is represented in the system, which is represented by a point in phase space, in the space of all its coordinates and its momenta, where is it located and how does it move as a function of time.
So like you take the separatrix case.
Yes.
In that take one of those whatever.
One of these lobes.
Yeah, one of
okay.
these lobes.
Uh-huh.
That itself is an entire phase trajectory, right?
That is a phase trajectory. So actually what is happening here, yes.
Only one lobe is a phase trajectory, the next lobe is a different phase trajectory.
Absolutely. This is a different phase trajectory from this. This is a different phase trajectory from this. This point is a phase trajectory by itself. So the statement is if you are here, then as t tends to plus infinity you are going to flow towards this point. If you started here and let t go backwards, you would flow towards this point. So that is the implication of what is meant by an unstable manifold and a stable manifold to a saddle point.
Where is it that point alone is phase trajectory?
Because that point alone is a solution to the system's equations of motion in which all the left hand sides vanish, and since these are first order differential equations, if all the initial conditions are 0, if all the derivatives are 0 to start with, then the system never takes off and it remains there. So that corresponds to taking this bob and balancing it at pi vertically up. Of course an infinitesimal displacement would cause it to move. So it is an unstable equilibrium, but it is an equilibrium point nevertheless. The crucial thing to note is that these separatrices, they actually qualitatively different kinds of motion are separated. Infinitesimally to the inside of it the motion is periodic, infinitesimally to the outside of it the motion is completely open, it is rotational motion as opposed to oscillatory motion. So they play clearly a very special role. What really happens is that in a system which is perturbed and non-integrable, unlike this system, the separatrices would really determine the fate of the system, dynamical system in some sense. Okay. Yeah. A homoclinic orbit was one where you started at a saddle point, made a loop and came back to the same saddle point. A heteroclinic orbit consists of more than one separatrix where you start at one saddle point, flow into another, you start at that saddle point and flow back to the original one. Could be more than 2 saddle points involved in this loop, but it is still a loop, and these loops get perturbed very easily, and that is how chaos appears in Hamiltonian systems. We resume with our discussion of the simple pendulum problem, in which recall the Hamiltonian h of theta comma p theta was p theta squared over 2ml squared plus the potential energy which is mgl into 1 minus cos theta, and we were specifically interested in finding out what the nature of the solution was as a function of time on the separatrix, which took you for instance from the saddle point at minus pi to the saddle point at plus pi in this fashion and back in this fashion, and of course you had small oscillations, larger amplitude oscillations inside, and this picture got repeated as you went along. We were interested in finding out what the explicit solution was on this trajectory here. On that particular trajectory, the energy had its value twice mgl, which is the maximum value of the potential energy, and we also saw that theta dot is proportional to cos theta over 2 on that trajectory. We saw this last time, and all you need to do is to integrate this. So this gives sec theta over 2 d theta is proportional to dt, and what is the integral of this? This leads to something like log tan theta plus pi over 4, and that is proportional to t on this side apart from some constants. Therefore theta can be written down explicitly in terms of tan inverse of the exponential of some time. If you sketch that solution as a function of t, then you discover that on that solution theta of 0, we took this to be equal to 0, theta of infinity was equal to pi, theta of minus infinity was equal to minus pi. It starts at this point and ends at that point, and we assume that it passes through theta equal to 0 at t equal to 0, and the solution looks like theta t here versus theta. It started at minus pi, passed through 0 and hit plus pi in this fashion. So it behaved like a kink, as if it had a kink, and if you compute the angular velocity corresponding to the same solution, here is t, here is theta dot, the angular velocity, this quantity is by and large 0 except it takes a sharp peak up here and then back to saturation value, and therefore it looks a little bit like that in this fashion, and this is like a lump. This quantity, this solution is related to what is called the soliton solution of the pendulum equation, of the Sine-Gordon equation, and this kind of lump solution, something which is essentially quiescent, nothing happens and then suddenly there is a little blip up there and then back down there to quiescence. This kind of thing is a special kind of soliton, it is called an instanton since it happens in time, but we are not going to get into this business right now, except to mention that phenomena like solitons are very characteristic of nonlinear equations, and the Sine-Gordon equation, as I mentioned, is a prototypical nonlinear equation which has a very large number of applications, and this is a very well known and famous solution of that equation. The point I want to make here is that in as simple a problem as the simple pendulum problem, it already makes its presence out here. Okay, now let us get back to our primary discussion, which was to understand what kind of phase space structure does an integrable Hamiltonian system have, and for this we go back all the way to a very simple 2 degree of freedom problem. So far we have discussed a few 1 degree of freedom problems. Now let us do something in 2 degrees of freedom, and we begin to see how things can get a little more complicated, and the model I have in mind is the 2-dimensional harmonic oscillator. You could imagine this to be 2 oscillators, simple harmonic oscillators at right angles to each other, which you are familiar with from elementary physics. I write down now the Hamiltonian, and since we have decided to call q and p the coordinates and momenta, so let me call this q1, q2, p1 and p2. This is equal to p1 squared over 2m, that is the kinetic energy of the first oscillator, plus 1/2 m omega 1 squared q1 squared, assuming the oscillator to have a mass m and a frequency omega 1, plus an identical expression over 2m plus 1/2 m omega 2 squared q2 squared for the second oscillator. This then is my Hamiltonian, and I have the characteristic, the typical Poisson bracket relations, namely q1 with q2 is 0, p1 with p2, q1 with p1 is 1, as is q2 with p2. So the 1 variables q1 and p1 have nothing to do with the 2 variables, they are completely independent dynamical variables. It is 2 uncoupled simple harmonic oscillators with in general different frequencies added together to form a 2 degree of freedom system in 4 dimensional phase space. The phase space is the space of the 4 variables q1, q2, p1, p2, each of which ranges from -infinity to infinity. So that is our set of the Hamiltonian of the system. What is the set of equations? Well, it is quite evident that they are just 2 decoupled oscillators, so we can write down the equations instantaneously. This is p1 over m and p1 dot equal to minus m omega 1 squared q1, and similarly for 2 with the subscript 2 replacing 1, so q2 dot is p2 over m, p2 dot is minus m q2. And of course each of these oscillators, if you imagine them to be at right angles to each other, oscillates maybe in a plane, the q1 q2 plane, completely orthogonal to each other. So the problem as it stands is completely integrable, it is solvable. Now let us apply the general results that we know to this case and ask whether we can say something about the nature of the phase space and what kind of motion we really have. We need for its integrability, since in this problem little n is equal to 2, the number of degrees of freedom, we need 2 functionally independent analytic constants of the motion. And of course it is not very hard to see that this combination here, which represents the energy of the first oscillator, is a constant of the motion, as is this combination here. And since the 1s and 2s have nothing to do with each other, this and that are in involution with each other. So you could in fact call this f1 and this f2, and f1 comma f2, the Poisson bracket vanishes, and each of these is a nice analytic function of the arguments, and therefore by the Liouville-Arnold theorem this system is integrable completely. We can write its solutions down explicitly. So let us formalize this. We have n equal to 2, and we could take f1 to be equal to p1 squared over 2m plus 1/2 m omega 1 squared q1 squared. In fact we could write fi is pi I and I equal to 1 or 2. We are guaranteed that f1 comma f2 is 0. Hence the system is integrable completely. Now we ask, what are the constants, what other constants of the motion could this system have? It is evident that the phase trajectories cannot be drawn by me since it requires 4-dimensional space, but we could draw the trajectories as projections of the trajectories into various subspaces. So for instance, if I try to draw the projection of the phase trajectory in the q1 p1 plane, for example, since it has nothing to do with this oscillator, it would just correspond to f1 equal to constant, which are ellipses as we know. Therefore you get phase trajectories of this kind, and similarly in the q2 p2 space you get ellipses of this kind. The periodicity here is 2 pi over omega 1 and 2 pi over omega 2 there. What would happen if we tried to project a trajectory onto the q1 q2 plane? What would you get? what would you get in general? Well, it is evident that Q1 for given initial conditions, it is clear that Q1 stays within this range and Q2 stays within that range. So the motion is restricted to some kind of rectangle, this being the amplitude in the first oscillator and this being the amplitude of the second oscillator, but is the representative point, is the projection of this trajectory, is it going to be a closed curve or is it going to be an open curve? It is certainly bounded, it is not going to go out of this region, but is it going to be closed or is it going to be open? It depends, absolutely right, it depends on the ratio of omega 1 to omega 2. If the ratio is rational, this means that the two periods are commensurate with each other, one of them is a rational multiple of the other, then it is clear the overall motion is periodic and the system given enough time will come back to its original point. Yes? In general you get Lissajous figures. Now the question is the Lissajous figure going to close on itself or is it going to be completely open? You are familiar from elementary physics with, for instance, depending on what the initial phase difference is between the oscillators, you would perhaps get pictures like this. You could get something like this, or you would get something like this, or you would get a pattern which fills up the space and never comes back to itself, depending on what the frequency ratio is. So it is clear, and we know this from elementary physics, that if omega 1 over omega 2 is rational, implies periodic motion. In other words, if we have two integers, say L and M, I don't want to use M because I have already used that for the mass, say K and L, such that K times omega 1 plus L times omega 2 equal to 0, it implies that the ratio is rational where K and L are integers, and then it is quite clear that the overall motion is periodic. But if no such relation exists with K and L being integers, then this ratio is irrational in general and the motion is not periodic. Although it continues to be periodic for the first oscillator and for this subsystem separately, we are now interested in whether the motion is periodic for the entire system or not. In other words, in the 4-dimensional phase space, does the point, representative point, come back to its original position? And the answer is no, not if the frequency ratio is incommensurate. If it is irrational, the motion is not periodic. Such motion, where the actual motion is made up of two or more mutually incommensurate time periods, is called quasi-periodic, and the motion in general is quasi-periodic in this case. So let me write this down. What can we say about the motion in this case? Well, here is where the general theorem I talked about helps us. The motion has to occur on a surface on which h is constant, since the total energy is constant. It is a Hamiltonian autonomous system. It also has to appear on a surface on which F1 is constant and on a surface on which F2 is constant simultaneously. And of course the Hamiltonian in this trivial case is just the sum of F1 and F2, it is not functionally independent of F1 and F2. We have just two functionally independent constants of the motion which are isolating integrals, namely F1 and F2. If we now go to action angle variables, and there is a standard method for finding the action variable in this case, it turns out that this Hamiltonian which we have written down here could be written in terms of action angle variables as follows. This Hamiltonian becomes I1 omega 1 plus I2 omega 2. where the two action variables I1 for example is an integral over P1 dq1 over a complete cycle. If the oscillator starts at the point say A and moves to B in the first oscillator, then it is an integral twice the integral from A to B of P dq, the corresponding P dq. So it is an integral over the orbit that I mentioned in the projection in the q1 q2 plane, and similarly for I2. And if you use those as your variables, and they can be shown to be canonical variables, then the Hamiltonian, this is what I call k of I, as promised does not depend on the angle variables but only on the action variables, and it is linear in the two action variables. You can easily check that the dimensionality is right, because action has the dimensions of energy multiplied by time and the frequency is inverse time. So the product of the two is has the dimensionality of energy. No angle variables are present here, and indeed you can see that in this simple case delta k over delta I sub I is in fact omega I, and the frequencies are independent of the amplitude of the motion because the Hamiltonian expressed in the action variables is linear in the action variables. Therefore when you differentiate it, there is no further dependence on the energy. We could therefore now go to a representation of the phase space in terms of the action angle variables themselves, and then what does it look like? Well, I know I1 is constant and I know I2 is constant, and this is the combination I1. This is like an ellipse in the q1 p1 plane, and an ellipse apart from units is topologically equivalent to a circle of some kind, and similarly in the q2 p2 plane this is an ellipse, and it is this combination that remains constant. That is again like an ellipse, which is again topologically equivalent to a circle. So I could in fact now identify what the angle variables are. Going back to P1 Q1, once I give you F1, in other words once I give you this ellipse, then the state of the system of the first oscillator is specified completely by specifying, for instance, what this angle is as the oscillator moves around, and similarly for the second oscillator. Therefore the state of the full system, once you give me F1 and F2, which depends on the initial conditions, is specified completely by specifying two angle variables, which in this problem can actually be identified with the phase of the oscillator in the q1 p1 and q2 p2 planes. What kind of space is spanned by two angles, each of which runs from 0 to 2 pi, two independent angles? It is a two dimensional space. What would that space be? Well, a rectangle, but with the ends identified, because 2 pi should be identified with 0 and the other 2 pi should be identified with 0. So he is completely right. It is like taking a square of length of side 2 pi this is a square of side 2 pi. So here 0 to 2 pi in the first angle variable theta 1 and 0 to 2 pi in the second angle theta 2, but I must identify that point with this and this point with this. I must further identify this point with that and this point with this. So I must take this piece of paper and roll it around and stick this, glue this onto that and glue that onto this. What happens if I just glue these two together, preserving the orientation? I get a cylinder. I take the cylinder and I preserve the orientation of the two ends and I glue them on and I get a two torus. So this is how the torus structure appears in the action angle space. So this phase space is nothing but the surface of a two torus in which I could measure theta 1 as the angle in this direction and theta 2 as the angle in the transverse direction, in the cross section of this torus, and any point on the surface of this two torus represents a state of this oscillator for prescribed initial conditions. In other words, the action variables, the size of the action variables is prescribed once and for all. Periodic motion would correspond to the following situation: as the representative point traverses in this direction a complete loop, it should do so an integer number of times in the other direction. That would be 1:2 or 1:3 or even 1:1 for instance. More generally, k times this period plus L times the other period, that they should be commensurate with each other. K times one period should be L times the other period, in other words the frequency ratio should be rational. In that case, this representative point which wanders on the surface of this torus returns to its original point and the motion is periodic. If the motion is 1:2 or 1:3, this simply means if it goes around here once, maybe it goes around in the other direction twice or thrice, it is hard for me to draw this, and comes back to the original point. The trajectory therefore would not fill this torus up, it would just be a curve on this torus folding around a few times like this, and then it does this, and then it does this, etc., and eventually comes back to the original point. On the other hand, if the frequency ratio is irrational, then we are guaranteed that the representative point never comes back to its original value precisely, but does so arbitrarily close to the original value an infinite number of times. The motion becomes quasi periodic. One way to see this would be to ask, let us imagine this frequency to be unity, and then we ask, how often does this representative point come and hit a cross section in this direction. So I take a cross section of this torus and I ask, here is the circle which represents the cross section. I start at some point here, so I am here, meanwhile it is going around in the other direction. When it comes back somewhere else and hits this cross section at some other point. It comes back a second time, it hits somewhere else, and so on. The question is, does it come back to the original value ever, or does it keep filling up this circle completely? It again depends on the frequency ratio, and we can prove the following theorem quite rigorously. Given a circle of unit circumference, if I add at each time step, I add a rational number, you are guaranteed that wherever you start, that point will be returned to in a finite amount of time after a finite number of iterations. Every point on the circle, whatever be the initial condition, is going to be revisited over and over again. All points are periodic points and the motion is periodic. On the other hand, if the number you add is irrational, modulo 1, because you are on a circle, then one can show rigorously that no starting point is going to be revisited. There are no periodic orbits at all. In fact, you can go further. You can show that the iterates of any starting point are going to eventually densely fill up this entire circle, and uniformly so. So it is not only important that it fills it up densely, but uniformly. There is no bias, there is no particular part of phase space which is preferred over other parts of phase space on this torus. So the iterates, the trajectory, any trajectory which starts here, will wind around this tightly till eventually it densely fills up. It is like a space filling curve, it densely fills up the torus but never comes back and closes on itself, comes arbitrarily close to its initial point many times, an infinite number of times, but never recurs, and the motion is quasi periodic. So this is characteristic of quasi periodic motion, that the system densely fills up a certain subspace of the phase space, and it is said to be ergodic on this torus. So quasi periodicity implies, to use a technical term, ergodicity on the torus. I repeat, by ergodic I mean that any initial set of any set of initial conditions, I take a little patch of initial conditions here. As time goes on, each of the points in this patch evolves in time, wanders around this torus. This little patch visits every neighborhood of this on this torus an infinite number of times, comes arbitrarily close to every starting point, and eventually fills up this entire torus uniformly and densely with no exceptions. It is said to be ergodic on the torus. What that implies is, if you want to compute long time averages of any physical quantity, you can replace the long time average by a statistical average with a uniform measure on this torus, a uniform probability distribution on this torus, and that is the implication of what this word ergodicity means. And in fact, you know that in statistical mechanics you normally replace time averages by ensemble averages, by statistical averages, and the distribution function has to be prescribed to you by the conditions under which the system is kept, and that implies a certain kind of ergodicity. It assumes that time averages can be replaced by statistical averages. And this is exactly what happens here in this dynamical system, which displays quasi periodicity here. We can go further. Our phase space is 4 dimensional. Any motion for given initial conditions is restricted to a 3 dimensional subspace of this 4 dimensional space, namely the energy surface. Now in a 3 dimensional space, the motion is further restricted in each case to a 2 dimensional surface, namely some kind of torus. And it is evident, if I try to draw this for instance, perhaps there is a torus here, and if I draw a cross section of it, it is like this. A different initial condition would correspond to a different torus of this kind, it would be like that for instance schematically. So the whole space, the energy surface, is simply filled up by these successive nested tori, and moreover, since phase trajectories cannot cross themselves, it is evident that if you start on one torus, you are never going to escape, you are going to be on that torus. If you start on a different torus, you remain on that torus. The gaps between these tori are also filled up completely by other tori, and that is the structure of the phase space for an integrable system like a 2 dimensional harmonic oscillator. But the matter is more general than that. Even more generally than this, if you have a 2 degree of freedom system which is completely integrable, then the motion in general is restricted always to some 2 dimensional torus. What would be the major difference between an arbitrary 2 degree of freedom integrable system with bounded motion and a harmonic oscillator? What is special about the harmonic oscillator? What is the feature that is absolutely special about the harmonic oscillator? You can't jump between tori, but that is true even for a nonlinear system, even in general this would be true, and that is simply a consequence of the fact that once you are on a torus, that represents a constant of the motion and you are on that surface. What is very special about the harmonic oscillator? The fact that the cross section is a circle, we are talking about topological aspects here, so the fact that the cross section is a circle instead of an ellipse and so on, this makes no difference, that is simply choice of units. What is particularly special about the harmonic oscillator? The equations of motion are linear, that is certainly true, it is not a non-linear system, but what is very special about it? Go back and recall that omega I was in general equal to delta k of I over delta I sub I. What happened in the case of a harmonic oscillator? It was constant, the frequencies were constant, independent of the initial conditions, independent of the energy of the oscillator, independent of the amplitude of oscillation. This feature is not true in general. In general, this is some function, this is equal to some function of all the action variables, and that would mean that the frequencies on the different tori would be different in general. It also immediately implies that if you have a nonlinear system of that kind, on certain tori, depending on what the values of the action variables were, because that is what determines the frequencies, frequency ratios could become commensurate, but you move to another torus, it could become incommensurate in general. So the motion could be actually periodic on some tori and aperiodic, quasi-periodic on other tori. Generically of course it would be quasi-periodic, but there could be accidental cases where you have resonances and the motion reduces to periodic motion on some tori. That is indeed what happens. What happens further is even more interesting. In a general 2 degree of freedom system, if the system starts out as integrable and you add to the Hamiltonian a small piece which takes you away from integrability and you lose the integrability property, then what happens is even more interesting. In general, this set of tori would no longer exist because it is no longer an integrable system, but in general it does not happen globally. In other words, first for certain sets of initial conditions, for certain delicately balanced frequency ratios, the tori get destroyed, the rational tori get destroyed first and gaps form between tori, and in those gaps the motion actually becomes irregular. It is no longer periodic or quasi-periodic, it becomes chaotic, and this happens when you have not an integrable system, but to an integrable system you add a small perturbation which destroys the property of integrability, and then typically you have chaotic behavior in the gaps between these tori. As you jack up the strength of this perturbation and make it go further and further away from an integrable system, in other words certain symmetries are destroyed more and more, then successive tori go on getting destroyed and still certain tori persist on which the frequency ratio is quote unquote extremely irrational. So now we are getting into number theoretic considerations and we have to discuss, we have to decide what is meant by a number being more irrational than another number. We will come to that in a second, and eventually all the tori get destroyed and the motion becomes completely chaotic, and we will talk about chaotic motion in much greater detail a little later, but this is the mechanism by which, this is a rough idea of what happens in such systems. In the same breath, let me mention that if you took an n degree of freedom system, for example n harmonic oscillators independent of each other, what would the motion be on? Well, the individual energies of these oscillators are n constants of the motion in involution with each other, so the system is integrable in the same sense. What would then decide where this representative point is? Just the angle variables, the individual phase angles of all the oscillators in the corresponding QP spaces. What would you represent that kind of phase space by? By an n torus, the generalization of a 2 torus to n dimensions, in which n angles would specify the state of the system, and then you could ask, is the motion quasi periodic on this n torus or is it periodic, and in general of course the answer is it would be quasi periodic, unless you had n minus 1 relations of the form k1 omega 1 plus L1 omega 2 plus etc. up to something times omega n equal to 0, and you had n minus 1 such relations between the frequencies. If you did, then all the frequency ratios are commensurate with each other and you have periodic motion. But if even one of them is lost and you do not have that relation, then you have some degree of quasi periodicity, and if you have no such relation at all with integer values of these parameters here, then the motion is completely quasi periodic on an n torus. I cannot draw a picture of an n torus. What I have done here is to draw a section of a 2 torus, and that is the best I can do on the blackboard, but you can easily conceive of the fact that you have motion on an n torus if the system is integrable. The phase space dimensionality is 2n, the energy surface dimensionality is 2n minus 1, and the torus is an n dimensional object. Now in 3 dimensional space it is clear that 2 dimensional objects such as these rubber tubes, they striate the entire space. You can put one inside the other and fill up this entire space. If you had, instead of 3 dimensions, if you had 4 dimensional space and you took these 2 dimensional objects here, they clearly do not fill up the space. There is no way in which the entire space is laminated by them. So it is evident immediately that if you took 3 or more degrees of freedom, n greater than or equal to 3, the phase space is 2n dimensional. the energy surface is 2n minus 1 dimensional. If the system is integrable, the motion occurs on an n torus in certain variables, and this is n dimensional. If n is 3, then this is a 3-dimensional object, this is a 5-dimensional object. The difference in dimensionality is 2, not 1. So it is clear 2 3-dimensional objects cannot separate this 5-dimensional space. Or to put it another way, in 3-dimensional space, if I have a 2-dimensional surface of this kind, a torus, there is an inside and an outside. It splits up this whole space into an inside and an outside. That is not possible if the dimensionality between the object you are considering and the dimensionality of the space is greater than 1. Is this clear? If I take 3-dimensional space and I draw an infinite plane in it, that is a 2-dimensional object, there is an up and a down, it splits the space into 2 parts. But if I took a straight line, which is a 1-dimensional object, it does not split 3-dimensional space into 2 parts at all. In exactly the same way, a 2n minus 1 dimensional energy surface cannot be split up into disjoint parts by n dimensional objects if n is greater than or equal to 3. When n is 2, this happens, because this is 2 and that is 3, and that is exactly the situation we looked at there. The implication is deep. The implication is these gaps here would all be connected to each other. There is no way you can have an inside and an outside unambiguously. All such gaps, you must imagine, would be connected to each other. There is enough room to go from one gap to another gap. And I already mentioned that once you have a perturbation which destroys integrability, then some tori get destroyed and part of the motion for some initial conditions becomes chaotic. But if the motion is chaotic in this region and this region is connected to all the other chaotic regions, this means that the chaos can spread. That all random motion, all chaotic motion in non-integrable Hamiltonian systems with 3 or more degrees of freedom, all such regions of chaotic motion are in general connected to each other, and they form what is called a stochastic web, and a kind of diffusion will occur over long time periods from one region to another. And this has profound implications in dynamical systems, especially in applications such as accelerator physics. This immediately makes a huge difference, because it's in some sense it says that regions where the dynamics is unstable, exponentially so, are actually spread out all over the phase space, not confined to certain regions of it. We will try to come back when we talk about chaos, we will come back to some implications, but the reason I digressed here was simply to point out that very simple arguments based on dimensionality can actually lead us to these conclusions, fairly wide general conclusions in this case. So having talked a little bit about quasi-periodicity, let us now take up a specific example. We go back a little bit and take up a 1 degree of freedom system where I show you explicitly how the nonlinearity plays a role and how time periods could actually depend, for instance, on the amplitude and the energy. And let us try to see if we can generalize the harmonic oscillator. So let us look once again at a 1-dimensional 1D nonlinear oscillator. I have a single degree of freedom, let us call it Q, and a conjugate momentum P, and the Hamiltonian in this case is h of Q and P, and this is equal to 1/2, let us write this as P squared over 2m, plus a potential energy. Let us fix the frequency of this oscillator, the natural frequency or some constant, to be equal to 1. So in suitable dimensions this thing here becomes Q to a power which is not 2. This is 2 would mean a harmonic oscillator, a linear harmonic oscillator, but let us in general have a power 2r, for instance, and let us set the mass to be equal to 1. So we just have this as the Hamiltonian divided by 2r. To start with, let us say r is a positive integer. So r equal to 1 implies simple harmonic oscillator, the linear harmonic oscillator. Well, we could write the equations of motion down immediately. And what would they be? As before, q dot is p over m and p dot is minus delta h over delta q. So this would be equal to minus 2r cancels, so q to the 2r minus 1. If r is greater than 1, it is clear this is a nonlinear system and a badly nonlinear one, because if r is 2, for example, this is already a q cube term and you can't linearize about the origin. Where are the critical points? The origin is the only critical point, so Cp at 0 0. What does the linear matrix say? If you linearize this, what would this be? This would become, yeah, this becomes 0 right here, and then what would happen here? You would get a matrix, a linear matrix. If I tried linearizing, I would get L equal to 0 1 over, oh, let us just take this to be 1, since I have chosen units such that the mass is 1. So this is 0, this is 1, and out here I get 0 and 0, because this is already a higher order term for r greater than 1. What would you say are the eigenvalues of that? 0 and 0, any triangular matrix, the eigenvalues sit on the diagonals. So this is in fact a degenerate case. We are not able to decide if the origin is a center or if it is some other kind of critical point based on linearization, simply because the system is degenerate, the critical point is degenerate. But let us take recourse to physics and ask what kind of system we have, and then I will point out a method by which we can decide that the origin is in fact a stable center, and we can do that very trivially in this problem by simply drawing the phase trajectories, q versus p. Yeah.
Aren't you taking a special case by taking r as a positive integer?
Yes, I am taking a special case by, the question is why am I restricting myself to r equal to a positive integer? I am going to relax this condition subsequently. So let us first take r equal to a positive integer, see what happens, draw some conclusions, and then we relax this condition, see what happens. Okay. What kind of phase trajectories do you get for this system? The way I have written it, it is clear that whatever phase trajectory I get, they are closed curves for all positive E, because these are all positive terms, each of these. It is completely symmetric about the q axis as well as the p axis. The motion is evidently restricted to some kind of rectangle, so we are going to get some kind of oval, this being the amplitude of the motion. When r is 1, of course it becomes an ellipse. When r is equal to 2, then you get p squared plus q4 equal to a constant, and that is a sort of squashed oval. By the way, what do you think will happen if r becomes larger and larger? What do you think will happen to this curve? We are plotting a curve, we are plotting a graph of this quantity equal to some constant E, which is positive, and what happens to this graph as r becomes larger and larger? In which direction is it going to get squashed? What is going to happen? It is evident that this amplitude restricts the total energy restricts this amplitude. This amplitude in fact is given by, if this is A, then it is quite clear that A to the 2r over r, 2r is in fact the energy, because the kinetic energy is 0 at these points. So what kind of graph would you get if r becomes larger and larger? I fix the energy and then I just change r, what happens? Would this ellipse become fatter like that, or would it become thinner in this fashion? What would it do? Yeah, it's clear. No, I fixed the amplitude. I fix this, I fix the energy and then ask what does this graph look like. I fix the amplitude and ask what does this look like.
You are talking about a particular set of initial conditions, right?
I am talking about, okay, let me be specific. I fix the amplitude and now I ask, I change this R, I increase it. I do the same problem for a different R. As R increases, what happens to this graph? It will do this, it will start doing this. As R increases, it will do this. Eventually as R tends to infinity, it would become the rectangle. Suppose R, we will take what he said a little seriously now, suppose R becomes smaller and smaller. If R is equal to 1, what would happen? Then of course you could say this term changes sign. If R becomes less than 1, for example, this term changes sign. We want to keep everything positive, so let us take modulus q to the 2r. What happens if R is equal to 1? It is just an ellipse. What happens if R is equal to a half? It is not a parabola. So let us go back, let us do a little bit of elementary calculus. I ask the question x over a to the power r plus y over b to the power r is equal to 1, and I want to plot this on the xy plane. What does this graph look like? A and b are some positive numbers. Since these are positive numbers, it is quite clear that the motion is restricted to some kind of rectangle of this kind. This is size A and this is B. When R is 2, this is an ellipse. So let me draw that. What if R is equal to 1? What kind of straight line? These are moduli. Absolutely, so it would be some curve like this. This is R equal to 1. What if R is equal to 4? It would get fatter and fatter, it would start doing this. And finally, this rectangle is the limiting case when R tends to infinity. What happens if R becomes less than 1? Yeah, absolutely, the curve starts getting concave, it starts doing this. So this would correspond to R less than 1. What happens if R tends to 0? Well, as R tends to 0, either x is equal to a and you are finished, or y is equal to b and you are finished, and the other variable must be 0. So it would be the axes themselves. It would be the axes themselves. So it would tend to this. So it is really a whole family of graphs that we are talking about here. The ellipse is just one such member of this family. So coming back to what we were doing, here is Q and P on this side. The phase trajectories are some kind of ovals, completely symmetrical in this fashion, and for every set of initial conditions you have a concentric oval of some kind, and these are the phase trajectories. A very nonlinear oscillator, and of course the system is integrable as it stands, simply because there is a constant of the motion, just the Hamiltonian itself in 1 degree of freedom, that suffices. It is some algebraic function of P and Q, and that is a constant. The motion is bounded, it is periodic motion, it is completely clear. What can we say about the time period of motion? How does it depend on the energy? How would we determine this? Of course, in the case R is equal to 1, the simple harmonic oscillator case, we could solve for P and Q explicitly, because the equations of motion were linear and you got trigonometric functions, and we know the time period of trigonometric functions, we know the periodicity. But what happens if it is nonlinear? What, for instance, would happen if R is equal to 2 or 3 or 4? What would happen? How would you determine the time period of this oscillator? Specifically, I would like to know how it depends on the energy of oscillation, on the total energy. What would one do in such a case? Well, you agree that the time period of motion by symmetry is 4 times the time it takes to go from there to there, and by symmetry it is just 4 times the time taken to go from here to here, or the oscillator to start at the origin and go to the end of its amplitude. So suppose the amplitude is A, and I look at this portion of the trajectory and I write the time period as equal to over the full orbit dt, 0 to t dt, but I could write this as equal to 0 to a dq over dt, which is q dot, but I must make sure about the sign of this quantity, which could either be plus or minus. It is positive in the upper half part of the diagram and negative here, and by symmetry, since we said it takes the same time to go from here to there as from there to here, this is equal to 4 times on this set to go from here to there, to go from 0 to the amplitude A, where by q dot I mean the positive square root of E minus this quantity apart from some constant factor. So this is proportional to, apart from some constants, numerical constants, it is proportional to 0 to a dq divided by q dot, but q dot squared, p squared by the way is just the same as q dot squared, since I have set the mass equal to 1, is E minus q to the power 2r. So this is square root of E minus q to the power 2r, apart from numerical constants 2r over 2r. But what is E for a given amplitude A? A to the 2r over 2r. So it is evident that this whole thing, keeping all factors of A present apart from some numerical constants, this goes like integral 0 to a dq over square root of a to the 2r minus q to the 2r. How are we going to evaluate this? For general positive integer r, this is not easy to evaluate, it is some complicated integral. You can't write this in simple form by any trigonometric substitution as you could in the case when r was equal to 1. Then of course you got a sine inverse and you could do the integral, but we do not need to do that. We need to only extract the dependence on the amplitude A. What should I do to extract this dependence? I could expand it binomially, integrate term by term and then reconstitute the whole thing, but there is a much simpler method by which you can extract the entire A dependence of t in one shot. Q is bounded between 0 and A, so what does that suggest to you? Well, the only length scale in the problem is A, we would like to know how t depends on A. So I should scale out this quantity A, so I put Q equal to AU, a change variable of integration, and then this implies that t is proportional to an integral from 0 to 1, a numerical integral dq, that gives me a factor a du divided by, I get an a to the 2r here which comes out of the square root and gives me an a to the power r. So a to the power r square root of 1 minus u to the power 2r. Multiplied by a numerical factor, that integral is guaranteed to be some finite number, because the only singularity which you have is at u equal to 1, and for instance if you had u to the power 4 here, then you have to worry about whether this integral exists or not, but you have 0 to 1 square root of du divided by square root of 1 minus u to the power 4, and that is an integrable singularity. Let me show you why. For instance, if you had 0 to 1 du over square root of 1 minus u squared, this of course could be written as 1 minus u times 1 plus u, and then you immediately see that this is the part that causes trouble at 1, not this, this is quite finite, and this is like dx over square root of x. When you integrate, the square root of x goes on top and the contribution at the upper limit vanishes. If you have a higher power like 1 minus u to the power 4 for instance, then that could be written as 1 minus u squared times 1 plus u squared, and once again it is only square root of 1 minus u that creates a problem, and this is true for every positive integer r. So the integral is actually finite, there is no difficulty at all, and it is some gamma function, it can be written down in terms of Euler gamma functions, etc. But what we are interested in physically is the dependence of the time period on the amplitude, and that is like 1 over a to the r minus 1. What happens when r is 1? It is independent of the amplitude, that is exactly what the harmonic oscillator is, but for all other r there is a dependence on r, on this index r. In fact, if you set r is equal to 2 and we have an oscillator which is a quartic oscillator, you have the Hamiltonian as p squared over 2 plus 1/4 q to the power 4. The time period of oscillation in this oscillator is proportional to 1 over the amplitude. In other words, the smaller the amplitude, the longer the time period. It seems counterintuitive, but why is it happening? Why is this happening? Why is the amplitude increasing as the amplitude decreases? And in fact, as the amplitude goes to 0, the time period is going to infinity. What is the reason this is happening? What is the shape of this potential energy? It is very flat at the origin, absolutely right. So if I plot V of q versus q, this potential has a third order minimum here, it is extremely flat. So as you come smaller and smaller, as the total energy decreases, the restoring force becomes smaller and smaller because it is extremely flat here. If you started with this much as the total energy, then by the time it gets here it has quite a lot of kinetic energy and it zips right past. But if you start here, it does not have enough kinetic energy to zip past this, and it rolls down this extremely slowly. And because it is not a simple minimum of the potential, it is not parabolic at that point, you have a diverging time period as a function of the amplitude. This is characteristic of nonlinear behavior. In this case, it is extremely flat, higher order minimum is immediately going to lead to such funny kinds of behavior. We are actually interested in finding out how the time period or the frequency changes as a function of the total energy of the system. How are we going to do that? We already have this result, t goes like 1 over a to the r minus 1. So how does it depend on the energy? Exactly, a to the power 2r is proportional to the energy, which implies that a is proportional to e to the power 1 over 2r, and that in turn implies that t goes like a to the power 1 minus r, which is a to the power 1 minus r over 2r, t e to the power 1 minus r over 2r. So that is the dependence on the energy of the time period. We could translate this to the frequency, and we will do this and see what the action variable is in this case, and we see how the tori actually depend, the size depends on the initial conditions in this case. So it is a very simple illustration of a nonlinear oscillator in which you have almost the same kind of structure as in the simple harmonic oscillator, but because it is nonlinear you have an actual dependence of the frequency of oscillation on the energy of the system. So let us stop here and then we take it from here. I recall that we were looking at the case of one dimensional motion in a nonlinear oscillator situation where the Hamiltonian, the function of q and p, was something of the form p squared over 2 plus q to the 2r over 2r, where r is a positive integer, and the case r equal to 1 corresponded to the simple harmonic oscillator. We had computed what the action was for motion in this potential, and we discovered that the action, which was an integral over p dq for bounded motion, oscillatory motion in this potential, was proportional to a certain power of the energy of the oscillator itself, which is e to the power r plus 1 over 2r. This is the result we obtained. Of course, if you translate this back to action angle variables the way we had defined it earlier, this implies that k, the Hamiltonian, as a function of the action is proportional to the action to the power 2r over r plus 1, which immediately implies that the frequency omega of motion, which is defined as delta k over delta I, is proportional to I to the power r minus 1 over r plus 1. Okay. If you therefore define a degree of nonlinearity alpha, say, and that is defined as delta log I over delta log omega, then this is equal to r minus 1 over r plus 1. And notice that r equal to 1, which is the simple harmonic oscillator, alpha is 0, no nonlinearity, and as r becomes larger and larger, the nonlinearity tends, as r tends to infinity, to the value unity. So it is a very useful indicator of the degree of nonlinearity, if you like, of an oscillator of this kind. Okay. Not a universal measure of any by any means, not a universal measure or anything like that, but a very useful one in many contexts. Okay. We also saw that the semi-classical quantization of this system is immediate. It follows at once, because if you recall, in semi-classical quantum mechanics, semi-classical quantization corresponds to writing I, which is integral p dq, equal to n times Planck's constant, where this is an integer. And if you take that along with this, this at once implies that n is proportional to the energy level E sub n to the power r plus 1 by 2r, or En is proportional to n to the power 2r over r plus 1. So it tells you something about the level spacing for quantized motion in this potential. Is it the other way about? Pardon? Ah, yes, of course, this is log omega over log I, and that is this degree of nonlinearity. Okay. The way the frequency changes as a function of the action. Thank you. So semi-classically we find that the energy level, the nth energy level, is dependent on the quantum number n in this one dimensional problem according to this relation here, valid for n much bigger than unity, which is where the semi-classical rule is valid. And again you notice that when r is equal to 1, so here r equal to 1, which is simple harmonic oscillations, we know that En is proportional to n itself. That is a level spacing which is equally spaced energy levels, and this is exactly what the harmonic oscillator does in quantum mechanics. Of course, the exact relation for En is n plus half times h cross omega, and the half arises from so called 0 point motion. The ground represents the ground state energy of the oscillator, but we are not going to get into quantum mechanics here. Just to point out that this semi-classical argument is immediately leads to this result, that En is proportional to this power of n for this whole family of potentials. Notice also that as r tends to infinity, we end up with En going like n squared, and that is precisely the level spacing for a potential which rises more and more steeply, infinitely steeply, namely a particle in a box. So this is exactly the same as the level spacing for a particle in a box, in a one-dimensional box. So that limit too is correctly obtained from this semi-classical formula. One can go further and actually try to find the correction to this n, corrections to other this quantity here, etc., but we are not going to get into that right now. So much for a little digression on semi-classical quantization, which follows from the arguments we have been giving here. Okay. Now let us go back a few steps and ask, what is the reason for having integrability in a Hamiltonian system? So we go back to n degrees of freedom, n freedom integrable Hamiltonian, and ask, what is the underlying physical reason for the existence of n constants of the motion f1 through fn in involution with each other?
The concept
Yes.
of freedom, in freedom,
Yes.
is it specific to Hamiltonian?
Yes, the way we have talked about it so far is a Hamiltonian system, the phase space variables come in pairs. So we identify n degrees of freedom, n independent degrees of freedom, which means that you must specify n numbers q1 through qn for me to tell me completely the configuration of the system in real space, if you like. And in addition, you need n conjugate momenta to complete the description of the system in phase space, in other words, to describe the dynamics of the system. So I call number of degrees of freedom the same as the number of generalized coordinates that I have, number of independent degrees of freedom. In the case of more general dynamical systems, first of all, the phase space does not have to be even dimensional. This pairwise structure, the Poisson bracket structure, is not necessary at all, and I do not distinguish between different kinds of variables. I just call the whole set dynamical variables, 1 to n, or as many as there are.
For example, in
Yeah.
statistical mechanics,
Yes.
relating to gases,
Yes,
ideal gases, we talk
Yes.
about ideal degrees of freedom.
absolutely.
But it's chaotic motion, as you said earlier. So what
Yes, absolutely.
degrees of freedom?
It's the same as the degrees of freedom. If I give you, for instance, in statistical mechanics, when you discuss monatomic gases, diatomic gases and so on, for a diatomic gas you ask how many degrees of freedom does a diatomic molecule have?
Chaotic motion, right? It's not Hamiltonian, it's some chaotic motion.
Yes,
So,
yes.
so whereas there's no concept of degrees of freedom.
The question is whether in chaotic motion the concept of degrees of freedom appears or not. Of course it does. It has absolutely nothing to do with the kind of motion. Identification of the number of degrees of freedom.
Establish that all sorts of chaotic motion which occurs in gases is Hamiltonian.
Yes, I would believe so. I would believe so, unless there are other reasons to believe that external forces are present, or there is a time dependent perturbation acting on the system, or anything like that. But if I give you a collection of molecules and you assume Newtonian mechanics to hold good, and the system is isolated, they act with forces acting upon each other caused by themselves, then I do not see why it is not a Hamiltonian system.
When you're not able to formulate the system itself, how can you generally say that it's Hamiltonian?
Why do you say I can't formulate the system?
You don't know the exact equation governing them, right?
I assume, let us assume, put a model on it, let us assume that Newton's equations are valid, let us assume that there is a certain potential energy between two molecules a certain distance apart. Once I have a model of that kind, I have a Hamiltonian system with a very large number of degrees of freedom, no doubt. The motion is in general chaotic, it is very irregular, it is not integrable. Yes, it is assumed to be Hamiltonian, yes indeed. Of course in real gases you have many other complications. For instance, you might have to bring in quantum mechanics, you might have to solve the entire problem quantum mechanically. That is a separate subject in itself, we are not going to get into that here, but otherwise yes, it is a Hamiltonian system. The kind of motion that a system has, whether it is regular or integrable or ergodic or chaotic, this has nothing to do with the identification of the number of degrees of freedom you have. absolutely nothing to do with it. So let us look at an n freedom Hamiltonian system for which the Liouville-Arnold criterion tells us that the system is integrable if you have n constants of the motion f1 to fn in involution. And then we saw that a transformation to action angle variables is possible, and once you make this transformation the Hamiltonian becomes independent of the angle variables, it is a function of the action variables alone, and then you can integrate the entire 2n set of equations that you have, all 2n equations for prescribed initial conditions, at least in principle you can do this. Now you could ask, what is the physical reason why this system is integrable, why these systems are integrable, what is the physical significance of these f1 through fn. Of course the action variables which we talked about, which lead to the natural frequencies of the system, the omega I, are certain combinations of these f's. So in that sense there is already some physical interpretation for these f's, but can we think of this in a slightly more physical fashion? Is there something much more immediate? And the answer is yes. The existence of these constants of the motion is related to some hidden symmetry in the problem, a certain dynamical symmetry in the problem. For instance, if I looked at two harmonic oscillators and the spring constants are the same in the two perpendicular directions, then you would immediately tell me that the Hamiltonian is rotationally invariant. You make any rotation in the xy plane and the Hamiltonian does not change at all. So there is a certain symmetry in the problem, and the existence of symmetry is linked to integrability. So whenever a system is integrable, whenever you have these constants of the motion, there exists a certain dynamical symmetry in the problem. Now let us try to understand what this dynamical symmetry is, at least go a little bit into this. It is a vast subject by itself, but let me at least give the rudiments of this subject. Let us go back and ask, what does a canonical transformation actually do to a system? So we start with a system with variables q, p, and you make a canonical transformation to a new set of variables capital Q and P. What does this do? What kind of transformation is it? Or if you like, if these Q's and P's are combined into a phase space variable x, a 2n dimensional vector, then these could similarly be combined into a 2n dimensional vector xi. These quantities are functions of these quantities which preserve the Poisson bracket structure. In other words, we know that Qi Qj is equal to Pi Pj is equal to 0, and we know that Qi Pj is equal to delta Ij. Now what is meant by a statement like this? What is meant, for example, by this statement here? What I mean by this is, this implies, if I write out this Poisson bracket explicitly, it implies that a summation from k equal to 1 to n over all degrees of freedom, delta Qi over delta Qk, delta Pi Pj over delta Pk minus delta Qi over delta Pk, delta Pj over delta Qk, this quantity is equal to the delta function. That is the definition of the Poisson bracket in the original coordinates, and if the Poisson bracket structure is preserved, it means you have a relation of this kind for every value of I and j. Similarly, we could write these down as well. Now is it possible to use this matrix J which we had introduced and write this in simpler form? Well, yes indeed, because you already know that I can write any Poisson bracket. I could write any Poisson bracket in more compact form if I use the J matrix. And what would that be? It would say, take this quantity Qi and take its derivatives, take the transpose of this, construct it into a row vector, put the J in between, and then the column vector from the derivatives of this, and that would be equal to delta Ij. Okay. So can we combine all these three relations into a single relation? And the answer is yes. Not surprisingly, it turns out that all these relations can be combined. Let me do that here. this whole set of relations is equivalent to saying that the Jacobian matrix of the transformation, which let me denote symbolically as delta xi over this delta x. By the way, this stands for the matrix delta qp over delta qp, this matrix transpose j times delta xi over delta x, this quantity is equal to j itself. It is easy to check that all these relations are summarized in the single line by this equation, this matrix equation. It is not very difficult to verify that this is so. I have used this symbolically just to tell us immediately that it is just the Jacobian matrix corresponding to the canonical transformation. Now what does this tell us? This quantity is a 2n by 2n matrix. Its transpose with a j in between times the matrix must be equal to j itself, the same matrix j, and recall that this j was equal to 0, the unit n by n matrix minus that and 0. It was a 2n by 2n matrix of this kind. What would you call a matrix such that its transpose times the matrix itself is equal to the unit matrix? What do you call a matrix which obeys this condition? Matrix transpose times the matrix, square matrix, equal to I itself. Well, if it is real, then it is an orthogonal matrix. This is the definition of an orthogonal matrix. The inverse of the matrix is equal to its transpose, that is an orthogonal matrix. If the matrix is restricted to real entries, then of course a unitary matrix is an orthogonal matrix because there is nothing to complex conjugate, but in general the matrix could have complex elements. In our cases here all these are real variables, therefore we do not have any complex elements, so a matrix of this kind is an orthogonal matrix. Can you give me an example of a transformation of coordinates, say, which is represented by an orthogonal matrix? Every rotation, absolutely right. Every rotation in physical space is represented by an orthogonal matrix. In 3-dimensional Euclidean space, any 3 by 3 orthogonal matrix of unit determinant represents a physical rotation of the coordinate system. The simplest of these, of course, as you are well aware, is if you took the xy axes and you went off to x prime and y prime at an angle alpha, then this rotation in the xy plane about the origin is represented by a 2 by 2 orthogonal matrix whose structure is what? What is the matrix representing this rotation? Absolutely, it is just cos alpha sin alpha minus sin alpha cos alpha, and so on in 3 dimensions. You can generalize this to higher dimensions. So orthogonal matrices with unit determinant, with determinant plus 1, represent physical rotations. Okay. That matrix there, which represents a canonical transformation in the 2n dimensional phase space, is not orthogonal because there is a j sitting here and a j sitting there, but by now we have got used to this j appearing everywhere in Hamiltonian dynamics. This is pseudo orthogonal in a certain sense. Such a matrix is called a symplectic matrix. Let me write that down. A matrix M transpose J, M equal to J. So this is some where M is a 2n by 2n matrix. Is called a symplectic matrix. So what is the lesson we learned from that equation there? Canonical transformations are represented by symplectic matrices. Just as rotations are represented by orthogonal matrices of unit determinant, canonical transformations are represented by symplectic matrices. Therefore, in exactly the same way that the study of orthogonal matrices tells you everything you need to know about rotations, in exactly the same way the study of symplectic matrices tells you everything you need to know about canonical transformations. So this is an algebraic approach to the study of canonical transformations. Now this kind of equation has remarkable properties, as we will see in a second. The first of which is the following: if I took the determinant on both sides, what is the determinant of J? J was defined by that matrix. The determinant of J is +1, we checked this out. So determinant J +1, and it turns out from this equation it follows, if I took the determinant of the left hand side, the determinant of a product of matrices is just the product of determinants, and the determinant of M transpose is the same as the determinant of M. So this tells you at once that this implies that determinant M is equal to ±1, because the square is equal to 1. It turns out that you can show without too much difficulty, although it is a non-trivial exercise, that the determinant of a symplectic matrix is in fact +1. This is why I mentioned earlier that canonical transformations also preserve orientation. They do not just preserve, they preserve a number of things, among other things they preserve orientation, but this is reflected in the fact that the determinant of a symplectic matrix is +1. Just as orthogonal matrices form a group, the product of two orthogonal matrices is also an orthogonal matrix. Every orthogonal matrix has an inverse and they form a group. In exactly the same way, the symplectic matrices of a given order form a group of matrices. This is a subgroup of the set of all 2n by 2n matrices which are non-singular. So let me write that down. The group of all 2n by 2n real matrices. So we are restricting ourselves to matrices which are real with real entries, 2n by 2n non-singular. What is a non-singular matrix? The determinant is not equal to 0. In other words, there is an inverse for the matrix. So the group of all 2n by 2n non-singular real matrices is denoted by GL, the general linear group of order 2n over the reals. So this stands for the general linear group. Among such matrices, the symplectic matrices form a subgroup of such matrices. In other words, the product of two symplectic matrices is again a symplectic matrix, all 2n by 2n for a given order. Okay. So it is a subgroup of this thing here, and this group is called the symplectic group, and it is denoted by SP 2n, and it is a subgroup of GL 2n. Therefore, for a given dynamical system with a given number of degrees of freedom n, the study of its canonical transformations amounts to the study of the symplectic group of the same order, of order 2n. Now a great deal is known about the properties of such matrices. So a great deal is known about the symplectic group and what it implies and what its generators are and so on and so forth. Therefore we have a fairly good idea of what the symmetry possessed by a system should be, a Hamiltonian system should be. Under a canonical transformation, a Hamiltonian flow goes to a Hamiltonian flow. Measure is preserved. What do you need for a symmetry of the system though? What do I mean by the dynamical symmetry of a system? What would you say is, given a dynamical system, what would you say is a dynamical symmetry of the system? One possibility is to look at its Hamiltonian, if it is a Hamiltonian system, and ask what kind of transformations leaves the Hamiltonian unchanged. That is one possibility. But of course in the case of a Hamiltonian system you need more than that. You actually must make sure that the transformations of coordinates of the variables is also canonical, so that the structure of Hamilton's equations is unchanged. The most general way of defining what the dynamical symmetry group of a dynamical system is to say a set of a transformation which leaves the solutions unchanged. Maybe takes one solution to another and it mixes up different solutions, but the solution space, the set of solutions of the dynamical equations should remain unchanged. That is what I would call a dynamical symmetry of a system. The full set of solutions must remain, of the dynamical equations must remain unchanged. If I accept that, then it is easy to see what I mean by the dynamical symmetry group of a Hamiltonian system, and let us write that down. By this I mean the dynamical symmetry group of a system is a set of transformations of its phase space variables set of transformations that leave the solution space pardon me, that is sorry I did not get the question. What is F? No, not necessarily. Not necessarily, there is nothing to do with the Hamiltonian system. Right now we are talking about a very general statement. I am simply saying when I have a dynamical system described by a set of differential equations and I ask what is meant by a symmetry group of the system, the most obvious statement is that it is a set of change of variables of the system such that the solutions do not get changed, the set of solutions does not get changed. That is what I would mean by dynamical symmetry group. Now let us come to a Hamiltonian system and ask what is the dynamical symmetry group of a Hamiltonian system, what can it possibly be? Well, what do you need for a Hamiltonian system's solutions to remain unchanged? First of all, I certainly need the following. I certainly need the Hamiltonian system, the Hamiltonian flow to go to a Hamiltonian flow. I certainly need that. This is done by the set of canonical transformations, but I need more than that. I would like to leave the solution space unchanged. In other words, the Hamiltonian itself should not change, so that the equations of motion are exactly the same in the new coordinates as they were in the old coordinates, right. So not only do I need the set of canonical transformations, but I need a subset of this group of canonical transformations which leave the Hamiltonian itself unchanged. In other words, I should not change from H to K, H must remain unchanged. That does not always happen with all canonical transformations. Therefore, the dynamical symmetry group of a Hamiltonian system, for a Hamiltonian system, the dynamical symmetry group is the subgroup of canonical transformations that leave H itself unchanged. So that not only do you go from a Hamiltonian flow to a Hamiltonian flow, but moreover it is the same Hamiltonian, and then you are guaranteed that the dynamical equations do not change, and therefore the space of solutions does not change either. In general, therefore, this dynamical symmetry group of a Hamiltonian system is a certain subgroup of SP2nr, whatever be the number of degrees of freedom. That also could be a group. It may not exist, you may not have much symmetry in the problem at all, and that is in fact what happens in general, but then in those cases where the Hamiltonian is integrable, it turns out that you have a dynamical symmetry group, and in fact that group is generated, the infinitesimal generators of these transformations that belong to the dynamical symmetry group are related to the constants of motion F1 through Fn.
That means that
So,
if you can get a transformation which is in the dynamical system group, its inverse should also be there. Like then you
yes,
will be generating
yes,
more.
of course, yes. In a group every element has an inverse, so this is certainly true. Yeah. Canonical transformations have inverses, that was our first premise, that going from the small q's and p's to the capital Q's and p's was actually invertible. This was our premise, that the canonical transformations we have talked about are global canonical transformations, namely they apply in all of the phase space concerned. Of course you could have a local canonical transformation which is not applicable in all of phase space, we have not looked at that possibility at all here. We are only talking about global canonical transformations, and they are certainly invertible. In fact, since you raise the point, a canonical transformation is a symplectic transformation, so it satisfies this relation here. And of course what does this imply at once? Let us take this m across to the other side by applying the inverse operator. So it immediately says mtj is equal to j m inverse, and let us bring the j to this side by applying the inverse of j, and therefore I get j inverse m transpose j is equal to m inverse, but I know that j inverse is minus j. J inverse is equal to j transpose is equal to minus j. So in fact I know that m inverse is equal to minus j m transpose j for a symplectic matrix, and therefore the inverse exists. No reason why it should not, its determinant we already saw was +1. So these transformations indeed form a group. The point I am making is that the dynamical symmetry group could be much smaller than this group, than the group of canonical transformations, could be much smaller in general, because I also pointed out that in cases where the system is not integrable you do not have any symmetry at all, but when you do have some special symmetry the system could become integrable. This is the idea here. Let me for example go back to the 2-dimensional harmonic oscillator and ask what the symmetry group could be. This is not easy to identify, it is not a trivial task to identify the dynamical symmetry group of a system which we know to be integrable. In general one has to do a little bit of work to do this. So let us look at the 2-dimensional oscillator, which is h of q1, p1, q2 and p2, and this was p1 squared plus q1 squared over 2 plus p2 squared plus q2 squared over 2 if I took an oscillator which has exactly the same frequency in the 1 and 2 directions. This is the isotropic oscillator here. This Hamiltonian has a great deal of symmetry. The symmetry group, the group of canonical transformations is the symplectic group in 2 degrees of freedom. So this is sp4 over the reals. what is the group of transformations that leaves this Hamiltonian unchanged? What would you say is a group of transformations that leaves this Hamiltonian itself unchanged? Notice that I can just take out the factor half and write this in this fashion. So I should write here 2D isotropic oscillator. Isotropic to mean that it's got exactly the same properties in all directions. As you can see, the potential energy is q1 squared plus q2 squared, which is invariant under rotations in the q1 q2 plane. So it has circular symmetry this kind. What would you say is the symmetry or the group of transformations of these 4 variables, each of which runs from minus infinity to infinity, that leaves H unchanged? We can switch variables, but there is a big huge continuous group of transformations. What would leave this unchanged, this combination unchanged? If I have x squared plus y squared plus z squared in 3 real variables x, y, z, what group of transformations leaves this unchanged? All rotations about the origin leave it unchanged in the 3 dimensions x, y and z. What leaves this unchanged? All rotations in phase space, in this 4-dimensional phase space, all possible rotations about the origin would leave this unchanged. What would that group be? The symmetry group of H itself. What would this group be? It is the group of rotations in 4 dimensions, 4 Euclidean dimensions. What would that group be? It is a group of 4 by 4 matrices, but what sort of matrices would these be? They have to be orthogonal. What should the determinant of the matrix be? +1, so volumes are left unchanged, and that group is a group of orthogonal transformations in 4 variables called O4, but because the determinant is 1, you write an S here to write special or unimodular, determinant +1. On the other hand, this stands for orthogonal. So on the one hand, the group of canonical transformations in 2 degrees of freedom is SP4R. The set of all 4 by 4 matrices with real elements which are symplectic, which satisfy that condition. On the other hand, this particular Hamiltonian is left unchanged by the group of all 4 by 4 matrices with real entries which are orthogonal and which have unit determinant. It is clear that for the dynamical symmetry group of this problem, the set of transformations in phase space that leaves this Hamiltonian unchanged and takes the Hamiltonian flow to a Hamiltonian flow, does not change the Poisson bracket structure, is that set of transformations which belongs to both this group as well as this group. In other words, the intersection of these 2 groups. So all matrices which are both symplectic as well as belong to this SO4, that set of transformations, that special subset of canonical transformations is in fact the symmetry group of this system. So as you can see, it is not easy to identify the symmetry group of a dynamical system, because not only must the transformation be canonical, but it should also preserve the form of the Hamiltonian. In this case, since the Hamiltonian was so simple, I could do this directly without too much trouble. I could just identify it by inspection. This looks like the surface of a sphere in 4 dimensions, and therefore I could immediately write down SO4. Now that group, which is the intersection of these 2 groups, is a different group altogether. It is smaller than either of these groups, and it is the group of, turns out to be the group of all 2 by 2 unitary matrices with determinant +1. So let me not write that down in explicit terms and get into group theory, but let me just write the result down and say the intersection is SU2, which stands for the group of all 2 by 2 unitary matrices with determinant +1. So it is a set of transformations which can be put into one-to-one correspondence with this set of matrices here, and this requires some mathematics to prove, which we will not prove, but I am going to simply assert that this is so. The reason I do so is because I would like to identify the generators of this group and show you what the physical meaning of these generators is. You see, what are the constants of the motion here? First of all, we know it is integrable. We had two constants of the motion which were in involution with each other, and what were those two constants? One of them was F1, which we could take to be just this, the energy of the first oscillator, and F2 was 1/2 q2 squared plus p2 squared. Okay. What else do you think is a constant of the motion here? It is clear the system is integrable. We know that the frequency ratio is unity in this case, the same frequency for both these oscillators. So on the surface of this torus we talked about the last time, when you go around the torus in this way once, you also go around this way once, exactly once. So the motion is periodic, completely periodic, there is just one period, unit frequency. These two are also in involution with each other. Now to describe the trajectory, you need one more constant of the motion, which is an isolating integral, so that the trajectory does not wind itself around on this torus completely, but rather is a discrete curve, is a curve, is an isolated curve for each set of initial conditions. What else do you think is constant in this problem? Let us think a little physically. Q1 let us say is the x axis and Q2 is the y axis, and you have got a problem where you have an isotropic oscillator, the same spring constant in both directions, and the potential is circularly symmetric. If I write this down in plane polar coordinates, this is just 1/2 r squared. So what do you think is constant in such a motion? Well, here is this particle in the q1 q2 plane. Well, the actual shape of the trajectory will depend on initial conditions, it will depend on what the phases are, what the initial values of q1 and q2 are, that is certainly true. But what do you think is a symmetry? I mean, what else is constant? What sort of force, if the particle is here and is attached by a spring to the center, what kind of force is exerted by the spring? In what direction is this force? It is always radial, therefore this is a central force problem. It is certainly a central force problem. What do you expect is constant in a central force problem? The angular momentum, that is right, there is no torque on this particle. The angular momentum is therefore a constant of the motion, we are guaranteed that. Now what is the angular momentum in this planar problem? You just have two variables, here is x and here is y, and this is p sub x and that is p sub y. What is the angular momentum? Well, if you use this formula r cross p, since you have reduced to a plane, everything is in a plane, this cross product is essentially a single number. So what is r cross p? There is only one component to it, and what is that equal to? Not P1, P2, Q1, Q2. Think in 3 dimensions. If you have r cross p in 3 dimensions, what is the z component of r cross p? What is the third component of the angular momentum, which I will call L? Or since I know that it is the third component, if I am looking at a 3-dimensional problem, let me just call it J3. What is this guy equal to? Yeah, it is equal to Q1 P2 minus let me put a half here for a reason which will become clear in a second. I am guaranteed that this quantity is a constant of the motion. In other words, the Poisson bracket of J3 with H is 0, that is not hard to verify. So indeed this is a constant of the motion, and now it turns out that the following quantities J1, J2 and J3, which we have already written as Q1 P2 minus Q2 P1, J1 is a quarter of Q1 squared plus P1 squared minus Q2 squared minus P2 squared, and this is a half Q1 Q2 plus P1, P2, it turns out that each of these quantities is a constant of the motion. So indeed it turns out that Ji, Jk or J, sorry, Ji with the Hamiltonian is 0, I equal to 1, 2 and 3. So we have other constants of the motion. These two together with this third one, the isolating integral, actually specifies the trajectory completely. The moment you put these three quantities equal to constant, then in this 4-dimensional space you found the trajectory completely, because the intersection, the mutual intersection of surfaces on which this and this are constant specifies a curve, and that is indeed the phase trajectory for any given initial set. Pardon me? J1 is a, yes, I am not saying they are independent, I am going to come to the significance of the J's a little later, but I am saying F1 plus F2 is the Hamiltonian itself, of course. For integrability you just need two constants of the motion which are independent of each other and which are in involution. They are represented for instance by F1 and F2, but I am actually finding a whole lot of other constants of the motion. For describing the motion you actually need three isolating integrals in this problem, and they are represented for example by F1, F2 and F3 and J3. But in addition these combinations are also constants of the motion. Sure, this is just F1 minus F2 apart from some constant factor. This is something else altogether, and this quantity here is the angular momentum about the origin. But now you can't have more than two constants of the motion in involution with each other, that is for sure. So in fact that is the maximum number that could be independent and in involution. You can choose them as you please with various linear combinations. I would like to choose this because this completely separates degree of freedom 1 from 2 altogether. The others mix it up in some fashion or the other. Now the significance of this J1, J2, J3 is that they obey very interesting Poisson bracket relations, and they obey the following relation. Among themselves you have J I J J is equal to epsilon I J K J K. This is the totally antisymmetric symbol in 3 dimensions. It is equal to +1 if I J K are a natural permutation or even permutation of 1, 2, 3, -1 if it is an odd permutation, and 0 in all other cases. This is the Levi-Civita symbol in 3 dimensions. So this stands for a set of 3 relations. J1 comma J2 is J3, J2 J3 is J1, and so on in cyclic permutation. What does this remind you of? This is exactly the relations obeyed by angular momentum components. If you write R cross P in 3 dimensions and ask what is the Poisson bracket of Lx with Ly or Ly with Lz or Lz with Lx, you get exactly this set of relations. So in some funny fashion angular momentum algebra in 3 dimensions is related to the dynamical symmetry group of the 2-dimensional isotropic oscillator, and the reason is group theoretical, it is purely algebraic. It turns out that this group is generated by 3 combinations of Q's and P's which are precisely these 3 quantities. They are, if you like, the generators of this group SU2. So you see what is happening is, to summarize things, here is a system which is completely integrable, it has 2 degrees of freedom. So we have 2 constants of the motion in involution with each other which are functionally independent of each other, and those are F1 and F2. Since the motion is periodic rather than quasi-periodic, we need a third isolating integral, another algebraic function of the Q's and P's, and that is provided by this quantity J3 for instance, which has the significance now of being the angular momentum about the origin. So we have the energy of the first oscillator, the energy of the second oscillator, and then the angular momentum about the origin. In addition, there are these combinations J1 and J2 such that J1, J2 and J3 are all constants of the motion, but they are not in involution with each other, they can't be, there are too many of them. Instead they obey a certain algebra. The Poisson bracket of any two is a linear combination of the same quantities, in this case just the third one with the appropriate sign. That algebra represents something much deeper. This algebra, the existence of this set of relations implies that there is a certain dynamical symmetry group in the problem which happens to be the intersection of the symplectic group SP4R of canonical transformations in this problem with the symmetry group of the Hamiltonian itself, which happens to be SO4, and that group can be put into one-to-one correspondence, the set of transformations, with the group of 2 by 2 unitary matrices, which is this group here, and this group has 3 generators which happen to be the same as that of angular momentum in 3 dimensions, and that is the reason why you have these combinations J1, J2, J3. So as you can see, dynamics and the algebraic structure underlying integrable equations, they are very closely linked with each other, and this 2-dimensional oscillator gives us a simple model in which to understand the origin of these symmetries in this case. Of course if you go to 3 dimensions and write the oscillator down in 3 dimensions, that is a much bigger group, the symmetry group is much bigger, the canonical transformations would be SP6 comma R, and then you would have to look at the intersection of that or the subgroup of that which also leaves the Hamiltonian unchanged, and that is a much more complicated group. Turns out that happens to be SU3 in that case, and so on. In fact the n-dimensional isotropic oscillator has a symmetry group which is the same as a set of transformations, the set of transformations that is the symmetry group is the same as the group of n by n unitary matrices with determinant +1, a very useful relationship in many applications. But I do not want to get into that right now. I would like to go back and give you another problem which also you are familiar with, where there is an extra symmetry, and we will see where this comes from. Yes, if the generators is 3, it is exactly the angular momentum algebra. This thing here is, no, it will not be. For example, the 3D isotropic oscillator, the dynamical symmetry group is SUN, SU3. In fact the general statement is the n-dimensional isotropic oscillator, n-dimensional isotropic oscillator. I should not call it n because this number n has been used for degrees of freedom, but okay, it is the same number actually, n-dimensional is SUN. So, no, it does not obey this algebra, it obeys a more complicated algebra, but the question you could ask is how many of these are there? That is something we can directly answer. How many generators do you think there are in SUN? Well, let us start from we could start from 1 by 1 matrices, and then we could go on to 2 by 2, 3 by 3 etc. The least trivial case is the simplest non-trivial case is SU2, so let us look at that. We want to look at all unitary matrices, 2 by 2 matrices which have unit determinant. I want to look at the set of all these matrices, and I permit complex entries. Okay, we will come back to what a generator is of a group, since I have to tell you how these groups are generated. What I mean by it is, let us come back and tell you what a generator is a little bit. I do not want to have a digression within a digression. So what is the number of parameters that you need to specify a 2 by 2 matrix? Start with a 2 by 2 matrix with possibly complex entries. We count the number of real parameters always, 8 parameters, because if the matrix is A, B, C, D and A and B are all A, B, C, D are complex numbers, there is a real part and an imaginary part to these. So in general 8 real parameters are needed. And now I start putting conditions on these matrices. What is a unitary matrix? A unitary matrix is one where U dagger U is equal to the identity matrix. So this is unitary. The dagger stands for the complex conjugate transpose, the Hermitian conjugate of this matrix. So I take the transpose and then do a complex conjugate of this matrix, and I insist that this be true. So what I am insisting upon is that A, B, C, D multiplied by the complex conjugate transpose. So this becomes C star, B star, A star and D star be equal to 1 0 0 1. I insist upon this. How many parameters are left now? How many conditions does this give me? Gives you 4 conditions. So how many conditions are left? How many parameters are left? 4 parameters are left. I now insist that the determinant of the matrix be equal to +1. That is what makes it S. How many parameters are left? 3, and therefore the number of generators is 3. In other words, any element of this group is found by taking certain special matrices, multiplying them by parameters and exponentiating these matrices, and that gives me a finite element, and that is called a generator of the group. So there are 3 generators, and that is exactly the number we found here, 3 generators. I will illustrate what is meant by generator in a minute, but now what do you think it is for SUN? What do you think it is going to be for n squared? It is n squared minus 1. Therefore in 3 dimensions it is 9 minus 1, which is 8 generators, and therefore there are 8 constants of the motion which obey a certain algebra among themselves, more complicated than this, considerably more complicated than this, but that provides you with a symmetry group. Now let us come to the question of what I mean by a generator, and let us go back and do a little bit of elementary algebra here. So I start with the simplest example of a rotation in 2 dimensions in a plane, and let us write the equations down directly. So I start with the xy plane and I make a rotation about an angle alpha to write new coordinates x prime and y prime, and of course I have x prime y prime is equal to a certain matrix acting on xy. This matrix here depends on the parameter alpha, and it tells me x prime is a certain linear combination of x and y prime is a certain linear combination of x and y, and it is well known of course that we have let us call this matrix which represents rotation by an angle alpha, let us call it R of alpha. Now what are the properties of R of alpha? What does a rotation do? It keeps the origin unchanged, it is linear, it is homogeneous, in other words 0 remains 0, the origin remains unchanged, and distances do not change, nor does this coordinate system become a left handed coordinate system. What is right handed remains right handed. So this means that this matrix R satisfies R transpose R equal to I, it is orthogonal which keeps distances unchanged, and the determinant of R equal to +1. Therefore this R of alpha is an element of a group of matrices which are orthogonal 2 by 2 matrices with real entries in this case and with determinant +1. How many parameters are needed to specify a rotation? 1. So this is a 1 parameter group and there is 1 generator. In 3 dimensions you have 3 Euler angles in general, therefore you have 3 generators for SO3. In n dimensions Euclidean space, how many generators do you need for specifying rotations? Yn. There are n axes or n angles, and this is precisely the point where I want to stop and we will take this up. That answer is not right because that tells you something about the nature of rotations itself. let me redefine a rotation. A rotation is a linear homogeneous transformation which keeps the origin unchanged, for instance, which is orthogonal, distances are not changed, and the determinant is +1. So a right handed system remains a right handed system. And the reason you say n is because you assume that every rotation is a transformation about some axis, and there are n axes, but this is not true, because if I think of 4 dimensions, then of course I could have a rotation which changes in the xy plane but leaves both the other 2 coordinates unchanged. Or if I look at 2 dimensions, there is no third axis, it is about a point. So an axis need not be identified with a rotation. That is an accident of 3 dimensions, it is an accident of odd dimensionality, we will come to that. So the number of generators is the number of independent orthogonal planes you can find. How many planes can you find in n dimensional space? Orthogonal planes like the x, y, y, z, etc. NC2, which is n times n minus 1 over 2, and that is the number of generators. So I will explain, this is a good example to explain what is meant by generators, so some elementary group theory, and then we will take it from this point. Okay. So let me write that down, SON I will explain what is meant by generator next time using this example. We'll take this.